Okay, good morning. So we can start with the first speaker of the day, Francoise Pène, mixing estimates for the periodic Lorentz gas flow in infinite horizon. Thank you.
Thank you very much, and thank you so much for the invitation. It's a pleasure. It's a pleasure to be here. So it's the second week for me. So maybe this talk will be better than the. So you are lucky. I hope. I hope it will not be worse. Okay. So the model I'm interested in is the ZD periodic Lorentz gas. So this name is in reference to a paper by Lorentz in 1995 to model the displacement of electrons in some metals. Okay, it's a Turing model. It does not exactly behave like that, but so the idea is so these are fixed atoms placed as ZD periodic position. And so how are these atoms that I will call obstacles? So I take them open because well, it will help me for the next definition of the space. Convex with C3 boundary and non-null curvature. So I take a finite number, O1, OI. So on the picture, I took just 2. Maybe I will need some colors. Okay. O1 here, O2 here, and they're translated. So O1 is here. It is a Z periodic model, and O2 is here. So, and then you consider their copy by translation by Z2, by ZD. So, and we consider that all these copies are pairwise disjoint, have pairwise closure disjoint. So which means that if IL is not equal to JL, then there is no point which belongs to the boundary of OI plus L, and also in the boundary. So this is L prime. This is empty. No cusp, no corner, no intersection. Okay, and we what is the displacement? So so this model, the dynamics is the following one. It describes the dynamics of a point particle moving at unit speed and respecting the classical Descartes reflection law, that is post-collisional angle are equal to pre-collisional. Okay, so you arrive like this with this angle, you go like this with the same angle. And I'm interested, okay. So what is the domain? The domain is either, well, I will write here. In R2, you take R2 minus these obstacles. And in here we are in R times the torus. We are on a cylinder, so there is the identification between this and this. You take the cylinder. So here L is in Z2. Here L is in Z, and then you identify this with L plus 0. And we make additional assumption. I will assume that the horizon is infinite. So, so fully infinite. So I will write what it means. What I call fully dimensional infinite horizon. So what does it mean? So in dimension 2, it means that there exist at least 2 non-parallel lines touching no obstacles. Okay, so you can see that on my picture, it's correct. There is one line here. And in fact, as soon as there is a line, there is not only a line. So this is supposed to be lines. Okay, you just imagine that my picture is perfect. There is in fact a corridor of lines. Each time there is a line, in fact, there is a corridor of line. There is one here, there is one here. Okay, so these two are non-parallel. This is fine. But usually, there are not only two. There is also, often, there are also diagonal ones. Another diagonal here. Okay, so there are, this is another corridor, this one. And there should be, maybe there is also one here. Okay. And they always are in finite number because the obstacle have some diameter, they have not a diameter 0. So then you have corridors. Or in fact, they are in finite number. And this is very important. That it's complicated enough. It's very important that they are in finite number. And in dimension 1, what does it mean? It means that there exists at least an infinite such line. What do I mean by infinite? Well, unbounded. I mean that it is a line which is not a circle. We don't care. Well, we don't care about having infinite or infinite horizon in this direction, but this will not be enough. What we want a well, there exists a non-vertical such line. Okay. So again, there are corridors, so the same. And the both of this model, you see, we can see them at a macroscopic level, where we just say, okay, so we just touch, we touch these obstacles, and we are in Z2 or in Z, and we can see it at a microscopic level. At microscopic level, I mean, you don't care about on which obstacle you arrive, where you are. You can just look at things modulo Z2 for the position. And then the dynamic is a Sinai billiard. And here, it's Sinai billiard in infinite horizon. Okay. So maybe I can draw a trajectory or try to draw a trajectory. Let's say I start from here, then I arrive here, and then I go there. And at time t, so I did not say what is the flow. The flow brings a couple speed position, which is in so what I called omega times S1. And if you want it to be very well defined, you just have to identify at a collision time this vector with this vector. So you divide by this identification. At time 0, to the couple position speed at time t. Just going straight. I forgot to say that. You go straight between obstacles. And the form of the obstacle is very important if you replace by rectangle, it's another word. Okay. Okay, so what can be said about the position at time t? So there is a result by Kasun over you. Which is in fact is a non-standard central limit theorem. So this result is the following: the position, so qt, at time t converges to Gaussian, but normalized by the square root of t log t. So converging in distribution, what does it mean? It means here that you take any probability measure at the beginning, you choose the point you choose your position and you choose your speed with respect to any probability you want, but you just assume it is absolutely continuous with respect to Lebesgue. So for example, a very small neighborhood of a point and a very small interval for the speed. This converges in distribution to a Gaussian random variable. So, okay, a small comment about the finite horizon case. In the finite horizon case, so meaning that there is no infinite line in any direction. There is no infinite line touching no obstacle. Then you just have a standard classical central limit theorem, which is position at time t divided by the square root of t converges in distribution with respect to a Gaussian. And by the way, something funny, because this is much simpler. Here, the asymptotic variance is given as this sum that I think has already been written in Vivian's talk, if I am correct. So some expectation with respect to some probability measure. This probability measure is a probability measure considering collision time only. So you have X here, okay. Okay, I drew another picture. You are in the Sinai billiard. So, yes, I did not draw the trajectory. I should have drawn it. So this is in the Lorentz gas. So looking at this, we start from approximately here. Okay. And then we go there and we arrive here. No, what do I do? We go there, and then we arrive here. And then we go, okay. So this is the Sinai billiard flow. But we can also consider the Sinai billiard map, which, so let's say we just consider collision time. Starting from here, we arrive here. So this is the Sinai billiard map. So the Sinai billiard map. And this map admits a probability measure, an invariant probability measure, absolutely continuous with respect to Lebesgue, and so invariant by the transformation. And this is this probability measure that appears here. Expectation of something. So how do I wrote it? I think here it's kappa. Okay, of some so this formula. So it's a bit complicated. I mean, it's a sum, an infinite sum. Here, there is an asymptotic variance. So I'll write it in dimension 1. In dimension 2, you just take the product, the well, so that you have here a matrix. Okay. You take the covariances. In the infinite, so I will write IH for infinite horizon and FH, but everything is in infinite horizon except this, in infinite horizon. So here, sigma, you have an explicit formula. What I mean by explicit, I'm more explicit than that. I mean that it only depends, it's either sum on the corridors. And it only depends, so it is a function, sigma of the length, what I can call length of corridors, or period of corridors, period, and width, the sum over the corridors. So I'm back to, okay, it's my musculation time. So here we have a corridors. This is its width. And what is this period? So we have these 2 points that correspond in the Sinai billiard. This is what I can call this period or its length, you see. Just a formula depending on something very geometric that you can compute really. No, you need to have 2, otherwise there will be a cancellation here. They did not write it, but this is really what will happen. Because then you will have for one coordinate and this normalization. Well, it's 2 extreme things. But you can see things in between. Okay. Or yes, you can see it covered. You will have a zero. Well, you will have a 0. Okay. So why is this difference of behavior? So the difference of behavior comes from the fact that when you think, so when you are interested in the position at time t, it's like looking in which copy. So at time t, you are somewhere here. Before you were on some cell, on some obstacle here. And this obstacle is a copy of some obstacle OI. So the position, when you divide by the square root of t, so it is not far away from this. Okay, and this, how can it be represented? This LT can be represented as a sum. So the idea is that when, okay. Well, maybe I will erase that because I always use a picture. Okay. So I'm starting from here. So let's say I'm starting from here. So before I was here, I'm arriving here. And when I do that, I make a change of cell. So I go from this copy -1, 0 to this one, 01 plus 0, 1. So what do I make? I make a plus -1, 1 at a macroscopic level when I just look at the label of the cell. So this is a function that we can define, kappa, change cell. And on our example, starting from this point, we arrive here. If we start from here, we arrive here because of the symmetry. Here, kappa is equal to -1, 1. And when you look things at a macroscopic level, where are you after n collision? The cell label is so the original one plus. So what you do, you add this kappa, and then you have to add the kappa starting from here. So what do you do? Since in fact it does not depend on the cell, in fact you are doing a Birkhoff sum on the Sinai billiard. k equals 0 to n minus 1. So this is this kappa that appears here, infinite measure. Okay. So in fact, it is related to some Birkhoff sum. Okay, kappa. Okay. Okay, so maybe this is not nice because it is random. It is the number of collision. In the time interval 0t, it is not very nice. But it behaves nicely because the number of collision, because of the Birkhoff theorem, because you have ergodicity, etc. So the ergodicity was proved by Sinai. Oh my God. Okay. The ergodicity of this model was proved by on the mixing. I should stay here. Okay. So I'm back here. Okay. So this behaves as so it's the number of times you go by some set. So for you, so it's well, it is Kack's theorem. Well, not well. Okay. It is the Birkhoff ergodic theorem, which tells you that it behaves. It is equivalent to t times the expectation of tau, where tau is the free flight. So the free flight between two collisions. So tau is not very. Voilà. Tau, in fact, is equal to, well, is related to kappa up to some boundary. So what do I mean? Okay, I will not do again. This is tau is this length. Kappa is the change of cell. You change cell, but it's not exactly equal to kappa, but it's very close. So you know that this is true almost surely. So using, okay, so it's very classical that then you can use t divided by, okay, you can use result of change of time. And in fact, it is enough to have a central limit theorem for with n instead of nt, just for the map. And so what we are saying is that behind this result, there is this. So sorry, there is k on kappa divided by the square root of n log n, which converges to a Gaussian. So why is it true? Intuition. So there is an intuition. It's that in this case, kappa is bounded. In the finite horizon case, kappa is bounded. Here, it is not the case. You can go as far as you can. You will not go to infinity starting from an obstacle because you are in a torus. So you know that either it's dense or it's periodic. So you will. It's not infinite, but nevertheless, it's not uniformly bounded. And you have this estimate, which means that it is what is called weak L2. So it is not in L2, but it is in L2 minus epsilon for all epsilon. In particular, it is integrable, so you have the right to write this. And so if you take some random variables, IID random variable which satisfy this, in fact, you have this central, non-standard central limit theorem. So this is a heuristic, this is not a proof. This is a heuristic argument explaining why it is not that surprising. Okay. So this is a central limit theorem. We wanted a local limit theorem. So we can call it a mixing result in infinite measure. If we are more probabilistic, we can call it a local limit theorem. If we prefer analyze, we can call it a vague convergence result. Okay, so depending on, and we can take these both names and say, okay, it's a mixing local limit theorem. Okay, so so what is the result? So this is the space M of our configuration. We take functions that are, well, I will write things, but it can be more general because of vague convergence result and the portmanteau theorem. You can take a lot of observables, not only this one. So I take vague convergence. It's about functions that are continuous and compactly supported. And the result is the following one. So it's about mixing. So what is mixing in a dynamical system? So you take a function, you multiply by the function, the other function with the dynamics. And so it is this result. So the normalization that appears here multiplied by the dimension. So we are in infinite measure. We do not say that the convergence decrease. We say that the integral decrease. Imagine that we are in infinite measure. There are a lot of space. So the time you spend, let's take, for example, okay, I finish, sorry. First, I finish the formula. So I'm saying that it's for continuous and compactly supported function, but it's also so true, for example, when you take for f and g, let's say you take a box for the position and you can take this. It's not continuous, but once you have vague convergence, thanks to the portmanteau theorem, you also have the result for this kind of function. So what does it mean? It means at the macroscopic level that you start from here at time 0, and then and you are back at time t in this. So this is small because you spend a lot of time somewhere else. And so mixing in infinite measure, instead of saying we take the covariance, well, I mean, even the covariance does not really make sense because one is not an integrable function. So subtracting one, well, you can, makes no sense. I mean, you take something integrable, you subtract one, and you have something which is not integrable anymore. So be careful about covariance in infinite measure. So here you just take this product, and with let's say two functions with positive. Well, the equivalent is written providing this is not 0. Okay. Otherwise, I have to write a small o plus. Okay. So just that. Okay. Non-zero. It's not equivalent when it is equal to 0. Okay. So why do I call it local limit theorem? I call it local limit theorem because when I take this particular function, so it means that starting from let's call B this starting from B, the probability that at time t we are in B behaves in this t log t for some constant. So this is a kind of local limit theorem in continuous time. In general, local limit theorem writes the probability that Sn is in some set. Here is the probability that phi t. So I will maybe give some just some other reference about previous work. Oh my God, I realized the bad thing. Yes, I prefer not to write it, but it's related to the sigma, which is here. There is an explicit formula with a determinant of the sigma. I mean, it's as usual in the local limit theorem. You have 1 over square root of 2 pi at the good power on the determinant. Well, it is a density. In fact, up to some constant of normalization, it is what appears is a density at 0 of the Gaussian random variable. It is always the case in, okay. Thank you for the question. Okay, donc some previous work about this kind of question. So mixing in ZD periodic Lorentz gas. So it appears that the finite horizon case is easier, even if it is complicated. So the result for the collision map, there are two difficulties: finite horizon and continuous time. This type of result does not go directly from discrete to continuous. Even if this is the way we will use, we will go using we will discretize the time. It's not that direct. Compared to the other one, the one of the central limit theorem, it is very classical to go from the discrete result, the discrete time result, to the continuous one. So there are two difficulties, two differences. First, collision map and flow, and finite horizon or infinite horizon. So this is the result for flow. So the previous result were in the finite horizon case by Sass and Voryu. So a bit before their paper on the infinite horizon. And for the flow by Dolgopiat and Andori. So you can appreciate the difference between the years. And then for both, here we are in a very nice situation because kappa is uniformly bounded. So we can also have expansion. So what do I mean by expansion? I mean that, well, an expansion of any order. So the result here is this behaves at n at the power d over 2. And then you can get something dependent on f and g plus n d over 2 plus 1. Okay, if I put here this in factor, another function, c1, fg, etc. And the same here. The same holds true for the flow. And again, it is not direct to go from one to the other. So, so this, I proved this, I do not remember when. Okay, does not matter. And so what does it mean? It means that, for example, if the integral of one of the function cancelled, but not of the other, this term disappears, and then you have the second one here. And you can have also the two, for example, if you take a commentary here, if you take f equal to h minus h composed with t, then the first term cancel as here because it has integral 0. But if h does not have integral 0 and if g does not have integral 0, then the second term does not vanish. But it can happen that you take a commentary of a commentary, or that g is itself a commentary. And so all the terms that appear here are linearly independent. You can have any order, in fact, in this sequence. And so the same for the flow, and this was proved combining, okay, with, I proved it with Dolgopiat and Andori. Again, I do not remember the year. I think I did not write it. Okay. Does not matter. A bit later. The collision, so, and for the infinite horizon, so in fact, when Sass and Voryu proved their results, they used transfer operator, and so they got also the local limit theorem in the same paper as above. Okay, so this is just some previous result. Okay. Okay. Maybe before going further, I can give you a toy model. What is a toy model for that? The The toy model for that is, okay. If you want to simplify things, because the billiard is a bit complicated, you have lots of dependents, even if they vanish, they disappear at larger scale. So the model is the following one. Take a random point. So let's say we start from this. Take a random point in the cell you have chosen. So imagine you have a way to choose a cell. You can choose a cell randomly. So you have some probability. So it can be Dirac. It can be I always start from the 0 cell. Then you choose a random point in the cell. And you choose two things. You choose a random change of cell. So I just take the same thing, but I take IID random variable, random change of cell. So what do I mean by a random change of cell? I mean that here I'm starting from some cell, the cell X, S0, and I will go to this cell. And what do I choose? I choose a plus X1, randomly, random variable. The one you want, I will tell you a bit, you take IID things. So you can choose a point so randomly here. And then you choose at the same time a random point in the arrival cell. So it means at a microscopic level, you choose to arrive here. And now what do you do? So you have Q0 here, Q0. And so here it's Q1 plus X1 that are what S1. S1 is your initial cell plus X1. So in fact, it will be at the end a sum of xk. Now you say, okay, so I will go from this point to this one. So go from Q0 to Q1 plus S1 at unit speed, because we are in a continuous time. So you move at unit speed. Okay. And then once you are here, up, you go here. You can choose again, next step, a new change of cell. You choose X2. So you were saying, how are the X2? So if you want a toy model for the finite horizon billiard, you take X2 bounded. If you want a toy model for the infinite horizon Lorentz gas, then you took X2 such that the probability then centered, xk IID centered. And in the domain of attraction, so each coordinate, first coordinate and second coordinate, I do not detect this, behaving like that. This is a toy model. So you can see something at a macroscopic level, in which cell I am. And in a microscopic level, it's not really IID, but it behaves asymptotically as a IID fic. Okay, so this is something that can be seen as a, well, Marco will maybe correct me, Levi Lorentz, okay. It is okay. It is not well, the usual one, but it is the spirit. But so this is a way to understand, I mean, to have a really probabilistic model with randomness at each step, which is the time model of that. Okay, and you go at unit speed. Okay. What is so? Okay, this is just so that you have something maybe simpler in mind that you can understand pretty well. So I will speak about the proof. And what is the difficulty here? The main issue. Well, there are several main issues. Okay. The main issue, well, there are several. Okay, let's just say one. One main issue. So the question is, I am starting from this part of the plane, so it is a true ball. And at time 0, I'm here, okay? But so I consider a configuration that is here. And what can happen? So is that in this box, there are configurations that can go to infinite. Okay. But this is not very important because you can neglect this. That's measure 0. But the problem, the real difficulty is that you have things that you cannot neglect. You have trajectories close to this one that can go arbitrary, really far away. It means that you do not know exactly on which obstacle you are and you were just before and after. We have in mind to discretize time, so to look at collision time. So when we are here, maybe it comes from a collision here, or from a collision here, or from a collision here, and there is an infinite number of possibilities. So this is a big issue. This existence of... So the proof consists in 2 steps. And in these 2 steps, we have different limit theorem. We needed different limit theorems. So we needed to prove them. It was not just, okay, they were written the good way, just use it. And so we have the first step. The first step, okay, so maybe I will be a bit vague for people who do not know suspension flow. And the first step is, let's forget this difficulty. Okay, I should have, okay, it's really my musculation. Okay, let's forget this problem and do not consider observable like that. Let's consider observable F and G supported on, what can I say? Well, to simplify, I can say there will be indicator offset. It does not mind. We are speaking about vague convergence. We don't care, which are very special things, which are small boxes here saying that you start from here and you do not go to infinite. Yes, you can go to infinite, but you are at a finite time. The previous collision. So this is, I can write it like that. It is phi of an interval, and this is a bounded interval of something which is on the boundary, on an obstacle. So at a bounded time in the past, you were on an obstacle. This is very particular. Okay, there are things like that here that absolutely do not have this form. So let's start with this. In the suspension flow representation, that we not detail, it means that it's a box like that. And the suspension flow is something like that. So it can go to infinite. Okay, okay, it's not bounded because this is okay. It can be like that. This is the collision time, and it's not bounded. But you are here in a finite. So you can also say, okay, if I have this, then I can also have this. Okay, no problem. But you cannot have something in the middle. I mean, in the middle, I mean here you have tau, which is big, and you are in the middle, I mean at tau over 2. This is not, you have to be at a bounded distance of a collision, at a bounding time of a collision. And these are very natural when you think about suspension flow, because this is compact for the suspension flow. So the difficulty here, one of the difficulty, is that compact for our flow do not coincide with compact with the suspension flow. So first step, the same results, but for F and G, compactly supported in the suspension flow, which means close to a collision time. So this gives non-natural sets such that, okay, we are here, but we cannot go this way. We have to come from, okay. So, so the result then what we did then, well, maybe I will come back. I will see if I have time. I'm not sure. And there is a second step, which is how can we go from this kind of observable to this one? So then we have to use a kind of tightness type result, saying that we can neglect that when we look to the flow, if we are over, so maybe over or below, I will precise, it does not, well, if this is larger than R, all this, in some sense, can be neglected. So I will write it. So this tightness type argument is, so I take for B a ball in the domain billiard, as I took, for example, you can take 0, 1. Well, it does not matter, something bounded. And I take for BR the points that are in this ball, but that will not in the R in a time R will not be on an obstacle. Okay. And so the tightness result is, so I can write it with lim sup, I will write it with a quantifier. So there exists a sequence epsilon r, a function epsilon r, such that for every r, there exists some time starting from which the Lebesgue measure of BR phi minus t of B, so which correspond to this integral. So we want to approximate our function by function like that. So we have to say that the error in between is neglectable. And this lemma is to say that this error in between is neglectable. So this is neglectable. So we want a normalization in t log t at the power d over 2. So neglectable means that there is in front some function epsilon r going to 0 as r goes to infinity. Okay, and so this is something that never appeared before because we were in bounded. Yes, you have a question? Yes, thank you. Thank you. Yes, yes. Otherwise, it would be easy. Did I forget it in my statement? Did I put a minus? There was a minus. Well, sometimes I write it on the left, sometimes on the right. So there is kind of, there can be some mistake at this place. So what is the idea? We are in a small cell like this. This is B times S1 with any direction. Here we make a big flight, which has length A, and this A should be larger than R. This is the fact that this point is in BR. And then we do things like that, okay? And we should be, at time t, we should be also back here. So here, by a flight of, so here you have a collision time, if you are a collision time. So I call x this point. So this one is t and x is t is a collision map. And so what does it mean? What does this mean? This means that what is the difficulty here? A difficulty here is that okay, so maybe I can write what does it mean. Saying that means that we start. Where did I write that? Okay. Where is it? Back 3, 4. Okay. It means that we start. So kappa. This should be okay. Maybe I okay. This means that the change of cell here was larger than A. Okay. Then what? That the free flight here is larger than B. Okay. What can we say about the change of cell from this to this one? So if A is large, obviously we are in a corridor, and there is a finite number of corridors. So there is one W1 like that, and one W2 like that, saying that in fact this displacement is I as this displacement is AW1 plus big O of 1. Maybe we are not exactly in the direction of the corridor, but up to an error of, and this displacement is B W2, where W2 is a unit direction of a corridor. W1 and W2 unit direction of corridors, of some corridors. So we want to be back in the zero cell. So it means that kappa n is a displacement. Kappa n is a change of cell between this and this. Here, the change of cell is, so at the end, the kappa n, so you take this kappa n. So did I write it the good way? Okay, this kappa n should be equal to this plus this. Okay, so what does it mean? Kappa n equals to AW1 plus BW2 up to an error of order 1. And what can be said about the time spent between this collision and this collision? So this tau n should be, so here we have time t, here the time is tau n, here the change of cell is kappa n, so the time is tau n, but then we have to so it's t, but we have to subtract minus A and B. Okay, so the idea is write it like that. Take a probability measure, take the sum over everything, A larger than something, let's say B larger than A larger than R. Then you sum over n, but it's an infinite sum. And then you sum on W1 and W2. This is finite. This does not care. It is finite. Here it is an infinite sum. So we have to avoid bad configuration. The one for which, so what do I wrote? A? No, okay. Okay. Well, it is infinite. Not really. It's not really infinite, but okay, that's right. It can be 0. It can be 1 because we have infinite. So, okay. Maybe I'm maybe I'm a bit too long. Okay, thank you very much. I hope it's a pleasure for you or not suffering. So we have to neglect the case when A is large. So this sum over every A, every B, and every N is very not nice. So we have to exclude this kind of case, which can be excluded using the fact that this estimate. Then we have to neglect the case when n is smaller than C1 of t for some small C1. So what we know is that the n typically has the same order as t divided by the expectation of tau. And to do that, so this is a large deviation estimate. And so we get the thing that the probability that n is smaller than C1t, which means that the number of collisions up to time C1t is larger than t. We get something like this. remember that we are in infinite horizon, so we are talking about large deviation for something which is not bounded. So does not, well, I mean, which is not L2. It's not that easy. You cannot write an exponential. Just exponential moment does not exist. This is enough for d equal 1. For d equal 2, it was not enough. So we had not only to consider this, but also the thing that the same probability, but saying that we start from the ball and come back to the ball. And in dimension 2, we get something like that, 1 over t log t. And then what do? You take this, you do a mixing local limit theorem. So the mixing local limit theorem tells you that it behaves as a product of all this. And here you have some power of n, log n. But this was not enough. This was enough for step 1. We also used in step 1 a mixing local limit theorem, writing also this sum. It was enough. But here we need a mixing local error with error terms. And the first error terms we got were not enough. We had to work a lot to have the good error terms. And in both cases, we also need a local large deviation, which is a result of this form. Probability that kappa n and tau n at the same time, and here also it is a local limit theorem for the couple, is in a bounded set. So there is an estimate like that, n log n at the power d plus 1 over 2 times log z. So remember that we are talking about non-square integrable thing. So this result was obtained with Ian Melbourne. So it was our motivation to look at this result. It was because it was a key ingredient to say that when we sum, that the sum, this tells us that the sum for n large here, that the sum for n large is neglectable. And for once we have the mixing local limit theorem here, we use Riemann sum for the sum on small n. Okay, sorry, I stop. Sorry. So it's perfect. There is no time anymore for question. Sorry. I did the. Sorry for being so long.
I'm happy to introduce Patrick Bernard and with the talk of the title Properties of Periodic Orbits for Generic Potentials. Thank you.
Thank you. So for a generic U, well, all periodic orbits, so it's rather weak actually, conclusion. All periodic orbits of energy 0 of H plus U are non-degenerate. So that's the statement. And so I will make immediately some comments because, so I don't know exactly in the audience, but this theorem actually already appeared in the literature, and I want to explain why there are some points which still needed some work. So maybe the first thing is that although you probably all know, I quickly recall what non-degenerate means because there are actually different definitions that could be given. So here, non-degenerate means, means that what I will call the linearized restricted return map So linearized just means that I take the differential of the flow, or that I take the linearized system along the orbit. And restricted just means that I consider it in restriction to the energy surface. So in other words, I take a section, I take the return map to the section, I differentiate, and I restrict to the energy surface. So I obtain a symplectic matrix in dimension 2D, and that's what I will always consider, and that's the reason why I started with dimension d+1. So sorry. So what does non-degenerate means? It means that this matrix does not have 1 as an eigenvalue. So actually, you can make a bit stronger conclusions, things like it does not have double eigenvalues, it does not have resonance properties, things like this. But although you probably all have that clearly in mind, I recall that you cannot hope to conclude that all orbits are hyperbolic, right? Because in the Hamiltonian world, in the conservative world, you cannot perturb usually elliptic systems to hyperbolic ones, elliptic linear matrices to hyperbolic linear matrices. Okay, so that was just to refresh that. And now some, say, bibliographical comments. So this statement, it appears as such in a paper of Oliveira in 2008 for t = 1, so in dimension 2. And then in a paper of Rifor and Ruggiero in 2012. But as I will now introduce, there's actually a missing ingredient in these papers. And my point is to explain what's the missing ingredient and how you feel it. So maybe in order to introduce that, I will make some history of statements of that kind that have been proved. No. Now, for such statement, compactness is not so important because you see a periodic orbit is compact actually. So up to countable things, it's not super important. Okay, so first remark is you could consider this statement in the case where H is reversible. For example, in the case where H is a Riemannian metric. Yes. H. So theta is my orbit. Of course, it can be any other number, yes. But I mean, what I mean is that you have to fix an energy value. You cannot obtain the same statement for all energies. So you have to fix beforehand an energy value. Or you could rephrase slightly differently. You could say that for a generic potential and for generic energy, all periodic orbits in these energy levels will be non-degenerate. But it's not true in general that for all energies, it will be non-degenerate. So so by the reversible case, I just mean the case where H of QP is identically equal to H of Q minus P. So this example is this class is particularly important for physical reason because it's the case if you take a Riemannian metric, right? So if you take a potential energy. And well, I just mentioned, okay, the theorem, of course, is also true in the reversible case. Why do I mention it? Because it's substantially easier in this case. I will come back to it. But still uncovered by the papers of Oliveira and Rifor, actually. A remark which is important is that if you start in the reversible case, then adding a potential will not take you out of the reversible case. So that's a kind of a subset in a subcase in itself. You cannot exit it by choosing an appropriate potential. Okay, so I just mentioned it for reference, for later reference. Then the same theorem for high energy. So what's the statement? The statement is that the conclusion is true on the open set of negative potential. So high energy means just that the energy is higher than the maximum of the potential. So on the open set, and actually that's what's proven by Oliveira and Rifo and Ruggiero. Okay. So a variant of that would be to consider a conformal bumpy metric theorem. So I state it rather loosely because it's just for reference. It would be saying that if you make a generic conformal perturbation of a Riemannian metric, you make it bumpy in the sense that all closed geodesics are non-degenerate. So conformal perturbation just means you multiply the metric by a positive function, right, of the base. So it's almost equivalent, this and this. And this actually, there's a paper of Contreras in 2010 in the Annals where he does not state that, but he introduces all the tools which are necessary to prove that. And then just to finish this, this story, there's the bumpy metric theorem. Which just says that a generic Riemannian metric only has non-degenerate periodic orbits. And just to fix the timescales, this is more or less, this is proven by, well, actually the literature is a bit confused, but there are papers from Abraham, from Klingenberg, Takens, that's in the 70s. And then there's a paper from Anosov in 82. So all these contains ingredients in the proof. I think there was partial proof, and probably full proof in Anosov. Okay. So actually, there are a lot of common aspects in all these results, and all the differences are contained in one of the steps of the proof, which is the so-called perturbation property. And so the question is quite the one you would expect. It is take a periodic orbit, make a perturbation which does not destroy it as a periodic orbit. To what extent can you change the return map? So so adapted potential, so I should say adapted perturbation. What do I mean? So fix an orbit theta, a periodic orbit. Now you look at only the perturbations. So in most cases, I will consider this will be potentials. In all the cases, well, except the bumpy metric, this will be functions on the base. And so among them, you take only those which are sufficiently flat on the orbit in order to not change the vector field on the orbit itself, but sufficiently non-flat in order to change the linearized system. So they are flat at first order, but not at second order. So you have a map. If you add a small potential, you will change the return map. And the question is, what can you say about this map? And what you would like is that this is an open map. In a sense, you can change that easily by changing that. So I put a question mark. So the question the main difficulty and the main difference between these different statements is to prove this property in the setting under consideration. Right. So this property is rather elementary in the bumpy metric theorem, and it's quite significantly more difficult if you just consider conformal perturbation, which is probably one of the explanation of the reason why there are several years between these two results. And then it's not actually very different to go from this setting to this setting, and then there's for this setting to this setting, and there's a new difficulty to go from this setting to this one, which is the one I want to discuss. Okay, so maybe I give so this is just to fix ID. Now I give a statement. So a proposition comes from the paper on reform Ruggiero, and also from an improvement of Lasrag reform Ruggiero, which appeared later, is the following one. So you give to yourself the Hamiltonian H, you give to yourself a periodic orbit, and for notation, I will denote Q and P its coordinates. You give to yourself a small time interval such that Q restricted to T0, T1 is an embedding. So the orbit is very nice here, even in projection. And you give to yourself U an open set intersecting so U is an open set in M on the base, intersecting the orbit segment that you will be considering. So if this is a drawing in M, imagine a piece of orbit, you have T0, you have T1, and you have, you can imagine U as something quite small like this. So these are the data. Now let me define E in C infinity of M as the set of potentials which are supported in U and which are what I call adapted, meaning that their differential is 0 on the orbit. Okay, so I'm just stating that this property holds in a more precise way, in a sense. So what I claim is that the map which from U in this vector space, which associates the transition map. So I take a section around this point and a section around this point. So I have a transition map. So this drawing is in projection on the base, but I think of the transition map as in the full configuration space. So this will be, once coordinates are chosen, a symplectic matrix, a 2D by 2D symplectic matrix. And what I claim is that this map, so actually Okay, let me continue on the other board. So what I claim is that so there are two conclusions, which are the two conclusions of the two papers. Actually, the second one is significantly harder. The first one is easier, so is sufficient. So I could just refrain to the first one, but the second one is much nicer to work with. So the first conclusion is that this map is a submersion on a dense open set. The problem, the difficulty, is that it's not a submersion everywhere. So it means it's kind of open, but not at the linear level. Not everywhere. And the second conclusion, which is proved in the second paper, is that it is actually open. So it's open, and in order to prove that it's open because it's not open at the linear level, you have to study it at the second order. So just to give a hint, the function it's x1 square minus x2 square from R2 to R is open, but it's not a submersion at 0, right? So that's typically what they do. They study the second order approximation on this map in the second paper, and they prove it has the appropriate shape so that the map is open. But this is really much harder than this. Okay, so for reference, in the earlier case, in the case of the bumpy metric theorem, this map was just a submersion, and so all these kind of difficulty did not appear. So not. So, okay, so there's a small difference that between what I call the perturbation property and between the statement that I give here. The small difference is that here, what I am studying is not the return map along the whole orbit, but the transition map along a small segment in the orbit. And this difference is what makes is what creates the difficulty actually. So I could call it the local perturbation property. So local in the sense that it's true on the orbit. It's not local in the functional space. It's local in the configuration space or in the phase space. It just says that if you take a small piece of orbit, you can control the transition along this small piece of orbit. Now, when you have that, you deduce the theorem for high energy by known methods. It's not trivial, but it's the same method as that was used earlier for the bumpy metric theorem. When you have the perturbation property, I'm not very ordered. Okay, so the idea is the scheme of proof that you should use for all these statements is the following. You have the local perturbation property. You would like to deduce the perturbation property, and then you deduce the theorem. So this is standard in the sense that it's the same method that was already used, for example, by Anosov that you can use. And this is the place that was overlooked. It's harder than expected. And the reason why it's harder than expected is actually very simple. The point is, in order to deduce the perturbation property for the local perturbation property, you should be able to find a small interval on your periodic orbits such that the rest of the orbit does not come and bother you above here. So this is again in projection. But you cannot always do that. That's a problem. And there's actually exactly one single case where you cannot do that is the case of what I would like to call round-trip orbits. So orbits which just go one way and back on the same path on the base. So V can exist. So this does not work immediately for round-trip orbits which follow back and forth, I think. Well, I don't know exactly what's this fourth word, but okay. Back and forth, the same path on the base. Except for these very special orbits, you can always find a small piece of orbit such that not only the orbit is embedded, but it's away from the projection of the rest of the orbit. Okay, so these are the ones. Okay, so the picture is in the base, you will have a segment like this. You go here and here, and so above, you would have something like this, right? So this is T star M. This is the projection. And this is M. And the derivative gets vertical above the extremities. Okay. So first remark is that in order for this orbit to exist, well, you see, it's easy to see that. So at the extremities, so okay. I'm lost in my board. Yeah, so these orbits cannot exist at high energies. So these can only exist below, at energies which are below the maximum of the potential. You just write what's the energy of the points where it turns back, and you arrive to this conclusion. So what do I erase now? Maybe this. So now, okay, so now when you are confronted with a problem like this, the existence of this very specific orbit, maybe the first reflex you have is thinking, okay, these orbits might exist, but it seems quite unlikely. So maybe if I first produce an appropriate perturbation by an appropriate potential, I will just destroy this structure, and then I can apply my perturbation theorem. But that's why the reversible case is interesting to have in mind, because in the reversible case, this kind of orbit have been well studied. You can study them by variational methods or things like this. They are called, for example, librations in the Russian literature, and they exist typically. So in the reversible case, the existence of round-trip orbits is typical. So of course, typical is not a super well-defined word, but what I can say more precisely is that they exist for open set of potentials. So you cannot get rid of them. So and once again, when you start in the reversible case, you are trapped in the reversible case. So if your data H is reversible, you are trapped in that. You will have, for many potentials, you will have reversible orbits, and you have to deal with them. Okay. So the first step then would be to do this case and to obtain a perturbation property for this case. So the remark is that the perturbation property, as I wrote it, is it here? Yes. does not actually hold for round trip orbits in the reversible case. So and I will try to convince you of this fact. So you take a periodic orbits. So of course, when you want to study the return map, usually you take a section and you take it more or less whenever you want, and it does not make a lot of difference. But in this case, in order to take advantage of the reversibility properties, things appear better if you take a section at a specific point where the orbit goes back. And so let T0 be one of the two times where Q dot of T0 is 0. And at this point, I take a section which is itself preserved by the reversibility, that is just the section P equals 0. And let sigma 0 is equal to P equals 0. Is it okay? It works? Or yes. So what I claim is, so the reversibility structure of the Hamiltonian implies that the return map phi, so once again, it's a map in SP. It's a linear symplectic map in dimension 2D. So I restrict to the energy surface, even if I did not really draw it here. So implies that this map is itself reversible. And what does it mean? It means that if you take R, phi, you get identity, where R is just the symmetry. So, well, okay, I always find the algebra of this reversible structure a bit non-intuitive, except when you are quite used to it. But that's the natural thing you would get from the fact that you can reverse the speed and follow the same trajectory. Okay, so now if I denote by SP R of 2D the reversible symplectic map, well, it turns out that SPR of 2D inside SP of 2D is an algebraic submanifold of positive codimension. It has empty interior. Okay, so now if you take if you take this map, which to a potential associates the return map, it will take values in it. And so it can be open with value. It cannot be open with values in the symplectic group of dimension 2D, because it takes value in a space which has no interior. Right? And what fixes that is what you expect. It's that this map is open with values in SPR of 2D. It is open into SPR of 2D. And this turns out to be enough because it's not very hard to check that inside this family of matrices, which actually is not a group, this set of matrices, those which have 1 as an eigenvalue are exceptional, form a closed set without interior, right? So from that you can use the same method as in the other theorems and conclude. So that would be the reversible perturbation property. Maybe I give some words about how you prove that. It's not extremely hard. Maybe I check time. It's okay. So how would you prove that? Okay, so I have this drawing. I'm going to do the drawing again. So I have the 2 points. I call them T0 and T1 when the speed vanishes and when the orbit returns. So I will take my section, sigma 0 and sigma 1. And in projection, I have an orbit which looks like this. And I will take perturbation located, for example, far away from the points where I return inside the interior of the orbit. Well, actually, no. Okay. Okay. So what's going to happen? How can you see the difficulty in this drawing? Well, what's going to happen is that you can apply the local perturbation property to understand the transition map from sigma 0 to sigma 1. So by the standard, well, not standard, but the known perturbation property, the map which you to a potential U supported in this open set associates the transition map from sigma 0 to sigma 1. So this is with values in as P of 2D, once you have chosen coordinates, is open. Of course, similarly, so if you did not know any relation between these 2 maps, the problem is that now you have your complete return map, which is the composition of these. So the composition, let me say, I'm turning this way, let's say. So I would, so the problem is, I would like only one of these to depend on U. That's what would make me happy, and that's what happened if you do not have this problem that the orbit is around triple orbit. But I cannot, because whenever I perturb this branch, necessarily I will perturb also this branch, which goes inside U. But here I can use the reversibility structure to understand this composition. The point is that the reversibility structure of the system gives me a relation between these 2 transitions. And the relation is as follows. The relation is, well, something similar to what I wrote earlier, is that so the symmetry composed with phi 1, 0 composed with the symmetry composed with phi 0, 1 is the identity. So once again, I don't want to spend a lot of time explaining this relation, but this is what's telling the fact that if you arrive here, change sign of the speed, and you will follow the same path back. Okay, so this gives me actually a relation between these 2 things, and I can explain this formula just according to one of them that which I know. So phi. So this I can write by saying phi 1, 0 is equal to R composed with phi 0, 1 minus 1 composed with R, if I'm not wrong. Remember that R is an involution. Yes? U belongs to, yes. So belongs to the space of potentials, which are supported inside this small neighborhood U, and which have zero differential on the orbit. So we are going to change the linearized transition map, but not the orbit itself. Okay. So just now, it means that well, I have a formula. It's nice to have a formula, then which is not too complicated, or which is that, let's write it like this: phi of u will be equal to, so let me r composed with phi 0, 1 minus 1 composed with r composed with phi 0, 1. And these two things demand, these are the same, and they depend on you. Okay. So now, well, it's purely a matter of understanding the space of reversible symplectic matrices. The point is that the map, which to a symplectic matrix M associates Rm minus 1 Rm, is actually a submersion onto the set of reversible symplectic matrices. Actually, it's easy to verify that this is reversible. Just make this. So well, onto is not so important, but more or less it's a submersion. So I'm done, because phi, the map which to U gives phi, well, I can compose it at decompose it as the map which to U gives the transition from 0 to 1, and then this map, which I maybe call it G. So my map is the composition of a submersion and an open map, so it's an open map. And so I'm done with the reversible case. So you have to check that, it's not very hard. So what now about the general case, the non-reversible case? So, well, you have kind of these two extremes which you have to deal with. One extreme is this idea that I mentioned first, that round trip orbit should not exist too often. And the other one being that in the reversible case, V exists, but you manage to deal with them because of the reversible structure. So the strategy for the general case is to introduce a certain property that the periodic orbits, the round trip orbits, may or not satisfy, in such a way that if they do not satisfy the property, you can destroy them. And if they do satisfy the property, you can deal with them by this kind of methods. So define, I would call them special round trip orbits in such a way that, well, you have two properties. The one is that special round trip orbits admit a perturbation property similar to the reversible one. So you can more or less do that with them. And second, for generic U, all round-trip orbits are special, which is just a rephrasement of what I said before. That is, if you have an orbit, a round-trip orbit, which is not special, you can choose a small potential in order to destroy it. To destroy it as a round-trip orbit in order to make it non-round-trip in a sense. Because you have, when you have a round-trip orbit, means that you have this and this, which project exactly on the same curve. So you have the feeling like I might make a perturbation in order that the will be different afterwards. Of course, there's a difficulty, which is I will perturb that and that by the same potential, because we project on the same place, and the potential depends on the projection. So that's why, for example, in the reversible case, I cannot do that. So I will, yeah, okay. So I have a bit of time, so I will try to, well, give you this definition, and that will be it. So yeah. So giving this, unfortunately, there's no, you have almost no choice with this definition, because if you want that it satisfies 1 and 2, it's basically given to you by the problem. It's quite a kind of almost a miracle that there exists such. But so it's a bit complicated for, let's say, superficial reason. The idea is that the linearized system along the orbit should be reversible. That's the idea. But actually, it's a bit more complicated you have to be a bit careful in stating it. So then, in order to state it, I will introduce some more facts. So there's a symmetry. So symmetry of the problem. So I make a small assumption, which is not important, and a priori, according to my definition, the Hamiltonian H might not achieve a minimum on each fiber, but I will assume that it does not make a whole difference. It's just simplifying. So I want that this function for each fixed Q has a minimum. Then it has a single one by convexity, and I call omega of Q this single minimum, and omega is a smooth section of the cotangent bundle. And it's a smooth section, which is important because what does it mean exactly that you are at the minimum of this function? It means that the graph, what I will call omega of this is precisely the set of points where the horizontal component of the speed is 0. So this is the horizontal component of the speed. So this is the set of points where round-trip orbits may turn back. So every round-trip orbit has to intersect this set. And that's why this assumption is irrelevant, because anyway, what bothers you will happen when this happens. Okay, so now I have a symmetry. When I have, if QP is not in omega, then there's a single point in the phase space at the same energy level for which the horizontal speed is parallel to the one at QP, but in the other direction. So there exists a single P prime such that two things hold. It's P prime is that at the same energy level as P, and the horizontal component of the vector fields are proportional. And actually, they are negatively proportional. So it's really this symmetry is really related to reversible orbit, because it says that the reversible orbit, if it goes through QP, it will also go through QP prime, because the second branch of the orbit is going at the only other point where the speed is proportional. Not in omega. Exactly. Thanks. And in order to understand why this is true, we're just a drawing. So a drawing in the fiber T star, in the fiber above Q. So I have my energy level, which is a convex set, not non-degenerate. I have a point here, and I want to find another point such that the differential is proportional to the one here. Well, I just take the parallel on the other side. So if this is P, this is P prime. And then, because they are negatively proportional, I can introduce the proportion coefficient. So this I call S, the map which to QP associates QP prime. And I introduce also the function S. So again, T star m minus omega with values in 0 plus infinity, which gives the proportionality coefficient. So it's just defined by the fact that H composed with S, dpH composed with S is equal to S dpH minus S. It's just the proportionality coefficient. So now I have a few properties of these objects. So the first one is just more an observation by property, but it's important to have in mind is that these do not depend on U. If you add U, you do not change that because this is defined fiber-wise. And if you add a potential, you will just translate the function H by a constant on each fiber. So you will not change these objects. So it's kind of a symmetry. Once you have given yourself the initial Hamiltonian H, you have given yourself this symmetric structure. The second is that you can extend that on omega. So small s can be extended by s equal 1 on omega to a locally Lipschitz function. From what? From what I investigated, you cannot do better. I would not make it a statement, but I convince myself, maybe with mistakes, that you cannot do better than this. And the third is that S can be extended to a C1 function map of T star M fixing omega. Of course, small s and large s are smooth outside of omega. The question is just extension at omega. And of course, a remark is that in the reversible case, you will have S equal 1 and S of QP equals Q minus P. So S is what I called R before the reverse. Okay, so now, now I'll just give. When I am supposed to stop, I have a few minutes or not? Yes. Yes. Okay. Fine. So, so I gave just now the definition of special. Of course, it's a not super interesting name, but a round trip orbit. So the round trip orbit is said theta is said special if so first thing, the symmetry coefficient should be identically equal to 1 on theta. So if you have a round trip orbit which goes back at a different speed from it goes, then this one you can destroy. It's not obvious at all. Well, to me. So ds is, so that's a bit barbarian, but I will explain, isoenergetically antisymplectic on theta. So if you look at R, it's antisymplectic. It's a map which reverses the symplectic form. So basically you would like ds to be antisymplectic, but actually you cannot get that. You can get that only in restriction to the energy surface. So either energetically means you restrict to the energy surface, to the linearized energy surface, so to the kernel of dH. Then you have a restricted symplectic form, and you want this restricted symplectic form to be sent to the restricted symplectic form at the other point. So here you have theta of t, you have the kernel of the energy, and here you have theta of sigma of t. Sigma of t is just the time such that they are at the same v project and the same point of the base. You have also the energy, and here you have a symplectic form. Here you also have the symplectic form. So in the restricted symplectic form, and you want that ds at point theta of t sends this to minus this. So that's almost reversibility, but unfortunately, you need to restrict. The statements will not be true if you just assume that ds is if you just stated the definition with ds antisymplectic. And the last thing is that you have a reversible relation. So once again, I take a piece of orbit in one side, and I will, maybe I call that S and T to not. Then I will have the piece going back on the same place of the projection. This I will call sigma of S. So once again, it is just the only time such that theta projects to the same point of the base. This I will call sigma of T. And what I want is the relation that, so ds at theta of t composed with the transition map from time s to time t in restriction. So I'm skipping a bit, that's complicating actually a bit the matters. Always I restrict to a section and to the energy surface, which actually is not completely innocent. But then, okay, so compose that, then with that, which should be ds at theta of sigma of s, and composed with phi from sigma of t to sigma of s. This should be identity. And for linear restricted, reduced, I would say. So reduced maps means here I choose a section, here I choose a section, but in order to express that, it's probably better to decide that I quotient by I don't choose a section, because otherwise I have to be here a bit careful about what section I choose, but rather I quotient by the vector field. So these are maps on the quotients of the quotient of the linearized energy surface by the vector field, so which is the symplectic reduction of the tangent space defined by the energy surface. Okay, and that's I I think that's it. So once you have this, because of this reversibility structure, you can do more or less exactly the same as here. And the hard part of the thing is to prove that if an orbit does not satisfy all these conditions, you can destroy it by a small perturbation, by potential. I'm done. Well, the convexity does play a role. For example, when I said, so for example, I said an orbit, either you can find a nice piece where it does not cover itself, or it's a round trip orbit. I think this this is not true in general. You could have, you could imagine some behavior more complicated of an orbit which would come, follow itself like this. Things, a more subtle way of not being able to disjoint the projection of a small segment from the rest. So I'm not sure you can do nothing. I think you can try to do things in the non-convex situation, but there are plenty of places where convexity is used. So I don't know, but it's reasonable to, well, it's a reasonable problem. Probably yes, but normally it's a bit easier. Yes, yeah. So I know there are some work studying that kind of perturbations, but just without watching it, just now I cannot tell you the answer to your questions. But I think, I mean, it's a reasonable question, and probably it's not so hard to get the answer of it. Yes. Well, finally, what can you avoid? What you can avoid is you can avoid a small set in the space of reversible symplectic matrices. So whatever. So if you give me a set which is invariant by conjugacy, so expressed just in terms of eigenvalues, and closed with empty interior in the space of reversible symplectic matrices, then you can avoid it. So I did not check to the end, but probably, so I'm sure you can avoid, for example, double eigenvalues, and probably you can avoid any resonance relations. But actually, this space, I didn't find in the literature this space being studied. So for example, you would like to have normal forms for reversible symplectic matrices, but I don't think they are known. Probably they exist. Probably it's a bit complicated, but I don't think they have been studied. So I'm not completely sure the answer of that, but almost. Yes, of course. Yeah, so it depends when you call resonance, what you call resonances. Yes, but yeah, it's always defined. What you call resonances for arbitrary matrices is not the same as what you call resonances for symplectic matrices. What you call resonances for symplectic matrices is those which are not unavoidable. So, but typically they will be like linear relations between, if you have eigenvalues of modulus 1 of the, there will be relations with the integral coefficients between the exponents. but yes, you have to group them by pairs and to take only one exponent by pair. Otherwise, you always have theta and minus theta, which is an unavoidable resonance.
So, first of all, before I start with my talk, I would like to thank the organizers for this beautiful workshop and the invitation to beautiful Pisa. It's always nice to be in Italy, even though the weather is not, but tomorrow, yeah. Okay, so I'm actually going to talk about a very classical theme, Lyapunov functions in dynamical systems. And this is joint work with Patrick Bernard, who just talked about something completely different, and Peter Giese, and Sigurdur Hafstein from the University of Reykjavik. So what do I want to talk? So what is the idea? I want to be quite general to sort of avoid questions of regularity of the underlying object. I look simply at a smooth manifold and X some continuous vector field. Especially what I mean is that the flow does not need to exist. So it does not need to be uniquely integrable. And then the question is, a very classical question, dissect M into two parts. I call this MI and MB, where the dynamics or the such that if I restrict, these are of course invariant, dissect into invariant, are such that, well, the dynamics of X to MI is what I would call interesting. And the restriction of X to MB is boring. And of course, people in dynamical systems, they are interested in this and less in this. So, and yeah, so, and what is the idea? To make this dissection is the following definition, which is probably by now 100 years old, is the following thing. We look at functions from M to R. And in this talk, they're smooth because is a Lyapunov function. If simply we have that the differential of t on x is smaller or equal than 0, and the first one, and second, if we know that if the differential at a point P does not vanish, then we actually know that this at point P is really negative. So if the differential, so whenever the differential is non-zero, we actually know that X is not in the kernel of the differential. And by this, of course, you just know that tau descends on X orbits. This is sort of the idea. To have some monotone property. This is something very, very typical in mathematics and physics. So, and the general credo here is that MI is the part where the differential vanishes, because that's where the interesting part happens. And the boring part is where the differential does not vanish. And you know this, for example, for Morse functions and their gradient flows. You have a torus like this and like this. You have the 4 critical points, which are exactly those parts where the differential, so I take f and x is minus the gradient of f. Then you know that the part where it vanishes, of course, are the critical points of f. And this is the interesting part, the current part would be called. And the boring part is there where the function is gradient-like, so where you know that the gradient lines really descend. So this is where it's gradient-like. Okay. So, and of course, since I said it's the classical, the names I should mention here in the Lyapunov on the classical dynamical system sides is, of course, Lyapunov, who gave name to the concept. And there's Auslander, who's in the 50s and 60s studied this for various reasons, also industrial application and military application. Then there's, of course, Conley and Hurley, who put their names on the existence or the first general existence results in the, not in the smooth case, but in the continuous case. And we should also mention the name of Dennis Sullivan, who wrote a paper in the 70s, where he sort of got very close to existence of these Lyapunov function, the smooth case, but his method sort of gave him only information on compact parts of the manifold. Here in general, I did not assume that the manifold is compact, but he did not really bother to extend it to the non-compact case, because I think at the baseline of it, he was not interested in these things. He was interested in other questions, which rather address compact manifolds. Okay, so this is the names, maybe names. Lyapunov, Auslander, Sullivan. Yeah. And historically, I think, no, I should. Conley is first, yeah. But then comes Sullivan, then Hurley. Okay, and there is a relation, which, this is the interesting part also in Sullivan's paper, was already noticed in the 70s by Sullivan, to general relativity. So there is a relation to general relativity, where these Lyapunov functions also appear, but under a completely different name. Their Lyapunov functions are time functions. Time functions just means you have a space-time, so you manifold with time and you put this together to a space. Preferably for physicists, it would be 4-dimensional. And you want on this space a global clock. Usually the basic thing about relativity is there is no universal clock, but you can make choices. And such a choice is exactly a time function. And of course, what you want from time, you want time to tick forward. You don't want it to stay still, which it would be if you have an interesting part in your space-time. Right? Then there, the time cannot, I will explain why, cannot tick forward. And those points you want to avoid, because it means basically you have no control over which direction time is flowing or time is flowing at all. So what do I mean by a time function here? In a Lorentzian manifold, you have, without defining it what it actually is, but the basic geometric structure is you have in each tangent space what's called the future cone, which is just the set of admissible tangent vectors to curves which model physical motions. The thing is, in general relativity opposed to classical mechanics, there's a limit speed. The limit speed is exactly attained at the boundary of this cone. So basically, everything that runs inside is slower than the speed of light. Everything outside is faster than the speed of light, therefore forbidden. And what's on the cone is exactly what travels with the speed of light. This is the photons, for example. And the function, a time function, is exactly something whose differentials are transversal to the to these cones. That means they are monotonous when you go inside the cone. They tick forward or backward. And this is just a matter of sign. So here the tau is actually negative. Okay, so working along this distinction here, the existence of a time function. So for relativists, a time function is really something that is everywhere, everywhere regular. So you don't have critical points. Everywhere regular. In opposition to what people are used to from dynamical systems, where this is really present, else you have a very, very boring dynamics. But physicists, they don't want this non-boring dynamics. They want something really there. So existence means no recurrence. And second, it was known already that the existence is tied what they call stable causality. And stable causality just means if you make the cones a bit wider, you suddenly don't have closed orbits which always go in the cone directions. This looks like recurrence, and it is actually also recurrence, because it's actually the exact analog to chain recurrence. In dynamical systems. Yeah? And do I mention the name? Yeah. This is actually Hawking. '68, I think. So the end of '60s, early '70s, which is interesting because you see, Conley was about the same time. And they were not aware of each other, but they're proving very similar things. There's a famous gap in Hawking's proof, but what Conley proved, he could prove as well. But they were not aware of each other until Sullivan noticed the similarity. He wrote the paper, which is actually published in Invenciones, so it should have caught some traction, but somehow it went under the radar until Albert Fatih and Antonio Siconolfi realized the relation again. Yeah, probably people were actually interested in something else in the entire matter. Yeah. Okay. So here the names one should mention in this business. On the Lorentzian side is, of course, Stephen Hawking. Then again, Sullivan. Same paper. Seifert, who tried to fill this gap. Then there's Rob Garage, who made some contributions in various aspects of the theory. Then finally, the final gap was then solved in the early 2000s by two Spanish mathematicians, Antonio Bernal and Miguel Sanchez. And what did they? And then, of course, a few years later, the relation between the theory of dynamical systems and time functions was dug up again by Albert Fatih and Antonio Siconolfi, who then wrote a paper that was actually properly noticed in the Lorentzian community. So, okay. No. Okay, so and the idea of Patrick and myself was a while back to sort of join these things together for more general structures towards existence, which we called cone structures, which is on one hand, the generalization of vector fields, and on the other side is also generalization of the Lorentzian metrics of these cones coming from these Lorentzian metrics. Okay. So, but when I want to talk about this, I have to, these cones, I need to introduce what I mean here exactly with recurrence in this context. Because this sort of at the beginning, between this stable causality condition coming from Lorentzian geometry and the chain recurrence in dynamical systems, there was no clear relation. It was sort of not super mysterious, but one needed to make up some concept in order to join them together. So this is recurrence and open cone fields. I will not go too deep into the definition, which is a bit technical at first sight. That's why I restricted to vector fields at the very beginning. But let me at least say what an open cone field is. So a subset of the tangent bundle of M is an open cone field. If two things happen, well, it's open, so it should be an open subset of the tangent space. And second, if I intersect E with an individual tangent space, should be it's an open subset, yeah, of the tangent space, that's for sure, but it should be a convex cone for all P and M. Okay. For example, think of such objects there and just take the open interior of them. Okay. Then maybe a remark here on this definition, sort of the pathological limit cases is that this intersection is empty, is allowed, and the second pathology is that this is actually the entire tangent space at some points. Yeah? Well, the second case will be prominent for the recurrence definition or for examples of recurrence, but these are allowed. And if we know that this is neither empty nor the entire tangent space, sorry, if it's not the entire tangent space, then we know that the zero vector is not part of the cone. So we might think of cones that always contain the vertex, but we want here to look at cones which do not contain the vertex. Because we want to make them bigger in the end, and then we get trouble at the zero, which I will give you in the next definition. It's what's an open enlargement. Definition. So, so such an open cone field, an open cone field E is an open enlargement of my vector field X. Which I took very general. If the following happens, I call it a set Cx is always contained in E for Cx defined by its intersection with the tangent spaces to be the positive multiples of x at the point P if this is non-zero, and the entire tangent space if the vector field there is zero. That's why I allowing this second option there. Okay, and since this is such an open cone field to a vector of open enlargement of a vector field which has zeros, then I know this is the entire tangent space on a neighborhood, of the zero locus of x. So if I have zeros of x and then take an open enlargement, necessarily by the openness, it must, this second here, this fact has to hold for p's in an open neighborhood of this locus. Which is sort of what you know from chain recurrence. Right? So if you have, look at a particular function, jump function for the chain recurrence definition, then you will have, and you have chain recurrence at some point, you will have chain recurrence for this particular function in the neighborhood of that point. Okay, but how do I model now chain recurrence in this, or recurrence in this context of cone fields? I borrow again a concept from relativity by defining what I mean by time-like curves. So see, so such a curve is E time-like because it depends on this open cone field there. If the differential at point T is always in this fiber of E above the point gamma T. So, and then, okay, then I have these sort of functions. So you can imagine you have your x. Let me draw an orbit of x. That's an x orbit here. Then I put myself somewhere on this orbit and take an open enlargement of this thing, which allows me to deviate a bit from the x, from this orbit. For example, by going this way, or this way, or this. These are E time-like curves. Okay. So what I learned from this, that if I look at what's called the chronological future relative to my open enlargement E of a point P, which is nothing but the Q's in M, such that there exists an E time-like curve gamma from, let's say, 0, 1 to M. Yeah, since these are cones, this is all in parametrization invariant, so that doesn't matter, which start at P and end at Q. So if I want to draw it in this example, with blue chart, for example, I would get something like this. If I'm lucky, yeah. It's a bit suggestive that this point here, P, should be in the boundary of the set, which is not always the case, but in the case we want to look at that are interesting to us, this is the case. So this is everything that's inside this blue wedge. And if you have a 0, then of course the things look different. This is when xp is non-zero. And if xp is 0, you basically get an entire neighborhood, which is, there's my blue chalk there. There's p, then this is the entire, contains an entire neighborhood. Yeah? Which is again something you know for this chain recurrence. Okay. So this is a bit of preparation and strange definitions. Now I call a point stably recurrent. So P and M is stably recurrent. That's the sort of the synthesis of chain recurrent and stably causal. If P is in the intersection of all chronological futures of itself for all open, E is an open enlargement of my vector field, let's say. So take all intersections of this, and if it's still in there, then it's stably recurrent. And then, of course, this depends only on x. So I can call this Rx the set of stably recurrent points. Maybe the first lesson one can draw is, this is actually was a question that only later appeared. Typical product of the pandemic, that the set of stably recurrent points is exactly the chain recurrent set. For your classical definition of chain recurrence for flows. And this, the point here is that if you have such an orbit as I drew there, the chain recurrence means that you start here, flow a while, and then you can jump, and then you flow, continue flowing. And this little jump, you can compensate by just perturbing your vector field, which is exactly meaning you make the possibilities of directions just bigger than an open set. So E plus of E of P. Now this is P. So that's this equivalence. Okay, but I said the important point are Lyapunov functions. So the existence theorem here is, this is actually where it started. But I mentioned it as the second one. I did, yeah. So if you have such a, let's see, it's not exactly how it's in the paper, Patrick. It's a bit different. But so a point is in the chain recurrent set, or in the stably recurrent set, if and only if for all Lyapunov functions, we know that the differential at P vanishes. So if it's not in a chain recurrent set, there's at least one smooth Lyapunov function, which is regular at that point. And second, there's an optimality. You can actually find a Lyapunov function, Lyapunov, such that the critical set of tau is exactly the stably recurrent set, or if you will, the chain recurrent set. Okay. So. Yeah. So maybe let me explain a bit the idea, because this is something that comes from Lorentzian geometry, and I'm not assuming that people in the audience are familiar with those ideas too much. So idea. Where does this come from? Let's assume that we have a point which is not in the stably recurrent set, which especially means that at that point, the vector field doesn't vanish. So by continuity, it does not vanish on a neighborhood. Okay. Basically what we have here, point P, XP, and then in the neighborhood, it sort of looks almost in the same direction. Okay, if these things are nowhere zero in this neighborhood, if I take an open enlargement, I can choose it that way that these cones are not too big. So for example, they are not the entire tangent space. Take cones like this. This is an example. So choose let me denote the open enlargements by such a symbol. Choose such that E of Q is proper for all Q and U. And proper just means it does not contain linear subspaces, or in that matter, it's not the entire tangent space. Okay. So now we call the definition of chain recurrent set, or that P is not in the chain recurrent set, and the stably recurrent set. It means that there is at least one open enlargement such that P does not appear in the future of E. So P is not in the chronological future of E, but that is always the case. P is in the boundary of this set. Remember, this thing is open. So it's sort of like a blue drawing. I have a P here. Then it looks like this. Yeah, this is I plus of E of P. And well, let me draw the boundary a bit. This is the interior. This is open, and the boundary looks like this. The boundary. And P is actually in there. Yeah? That's important because this thing, note that this thing is a locally Lipschitz hypersurface. What do I mean by that? Around every point, I can find a chart such that in this neighborhood, or this chart neighborhood, the boundary is the graph of a Lipschitz continuous function. So this drawing here is not so far from the truth. Right? This is what people knew classically in Lorentzian geometry. Okay. But if you have such an object, such a locally Lipschitz continuous hypersurface, you can smooth it. So let me draw it like this. This is the boundary of our future here of P. I can smooth it. Smoothing. What I need. Yeah. Plus an interpolation. So smoothing means I just smooth it to a smooth hypersurface such that P is still in there, which is then, let's call this HP. And I can extend this, which is still transversal to E. Yeah, so the tangent spaces do not contain any points in E. And I can extend this locally to a foliation around this hypersurface, which is still transversal to the E's. I might have to make the E's a bit smaller. Yeah, I have to restrict the cones a bit, but it's still possible. It still contains X. So if I have such a foliation, I get a Lyapunov function which is regular near P. By simply declaring those hypersurfaces to be level sets of my Lyapunov function, making them maybe 1 here and -1 here, or the other way around, 1 here and -1 here. And that gives me Lyapunov function. So I get a Lyapunov function. Call this tau P, regular at P. Okay. And then we can sum over a locally finite over a locally finite cover of the complement of the stably recall. It's an open subset. Yeah? This is a closed subset. This is open. We can sum over it. And we can actually choose coefficients such that the sum over such Lyapunov function still stays smooth. It's actually probably classical theorem, but nobody before Albert Fatih bothered to write it down. So there exists AI positive such that the number AI, tau pi, is still a smooth Lyapunov function. And since they are positive, this will still be a Lyapunov function. Okay, that actually shows that the intersection of all Lyapunov functions, the critical sets, are contained in the stably recurrent set, and the other way around is follows from, so the other implication follows from the fact from that the intersection of such things, such open enlargements in the chronological future is actually contained in the sublevel set of tau being smaller or equal than tau of p for all Lyapunov functions. So that gives me basically the existence of result up there. And then there's a theorem of Sigurdur and myself a little later that actually says there exists a complete Lyapunov function, which is sort of the best one can hope for. What is that? Lyapunov function tau bar, let's say, from M to R, smooth, of course, such that the critical set of tau bar is exactly the stably recurrent set. What do I mean by complete here? That just means so tau bar complete. That definition if two things are satisfied. If I take pre-image of a value of tau and intersect it with the stably recurrent set, this is a chain transitive component or stably transitive component, which is the same thing, yeah. Component. That was actually already in the theorem by Patrick and myself earlier. But the part what we did not look at was that the image of the stably recurrent set is nowhere dense, which is not, doesn't follow immediately from there. But you can work a bit to sort of, what you have to do is when you have critical values, you have to pull them a bit apart. You have to squeeze a bit of real line in there, which is a bit of a technical fiddling. Okay. And the starting point of the discussion with Peter and Sigurdur was that these people they are two applied mathematicians, so they actually do numerics from the Lyapunov function. So they want to calculate them in the computer. And they asked me, can you actually control the differential of a Lyapunov function outside of the recurrent set? And of course, you cannot do this globally. Yeah? This would be asked too much. But if you give yourself a bit of space, then you can do it. This is maybe my last statement. So if you have a continuous vector field and a compact subset of the complement of the stably recurrent set, be given, let be Yes. And G a smooth function on M to the negative real numbers. Remember, we want Lyapunov functions to descend. Then there exists, we call this tau k, for k this compact set. Maybe do that add in G, or no, I did not add in G, which is completely Lyapunov. For X, of course, such that, yeah, again, the critical points are exactly the stably recurrent set. And the interesting part here would be to get the G into the game, which just means the differential of the Lyapunov function evaluated on the vector field restricted to K is exactly this given function on K. So you can sort of prescribe how much this Lyapunov function descends on this compact subset. This is what the numerics people are interested in, because they say, well, you have this beautiful, nice existence result for Lyapunov functions, but our computers, they have a machine epsilon. Yeah? So and since you cannot control by the pure existence how fast this descent is, you need a threshold for this descent. You know? And for them to determine that some point does not belong to the stably recurrent set, they need this G, for example, to be 1, yeah, whatever. Okay, so that was interesting to them. We'll see how this will take us in the future. Maybe one word for the theoretical part with Patrick. The next step would be we're trying to do is to generalize these existence results to so-called Lyapunov 1 forms, which gives a better control of basically the dynamics, yeah, that are non-contractible or non-homologous. Okay, thank you.
Thank you very much for the presentation. Let me first thank the organizer for this kind invitation. It's a pleasure to be here. Let me say that I'm a physicist, and so my talk will be a little bit different from the talk that you have followed up to now. No, but I'm just saying. And in this talk, as you have read from the title, I will talk about a topic that has attracted the physical literature in the past 10 years, roughly. This topic is about stochastic Suhr processes, and in particular is about the seemingly paradoxical result according to which if you want to speed up a Suhr process, sometimes it is better to restart it and restart it from the beginning and start it again. Okay, just let me give first a little bit of context. As you may already be aware, there are a lot of natural systems ranging from the microscopic world to the macroscopic world. When one has to study or is interested in observing randomly an object that has some complex dynamics, that has to reach, let's say, a given threshold or a given point in space. And for example, you may think of this like in system, like in a chemical system, such as, I don't know, binding or trapping in molecular environment, or diffusion controlled chemical reaction, or either you can think of animal looking for food. And there are a plethora of such examples. There are books written on this topic and application of stochastic process on search process. And of course, from a practical point of view, the question of interest is often the efficiency with which the search is done. let's say the efficiency with which the given target is reached. And a very rough estimate, let's say, no, a very rough measure of this efficiency is that, for example, the average time with which the search is completed, roughly speaking, because if you do an experiment and you repeat it many times, you want to know on average how much time do you have to wait before the experiment is completed. And of course, a question of interest is if there are strategies to improve this search efficiency, if there are ways to reduce or minimize the average time for a completion. And as I said at the beginning, in the last few years, has been observed that in many cases, a valid strategy consists in interrupting the search and restart the process from the beginning and repeat this procedure many times until the target is finally reached. And this has been called resetting or restart, and in many cases is reference to study of first passage process under restart, and so on and so forth. Let me just mention that this resetting strategy can be thought of as something that you can artificially do, impose on the system, but there are also cases where this is implemented naturally. For example, here I'm presenting you this renowned Michaelis-Menten reaction scheme, which is a very basic scheme for a chemical reaction, which you have an enzyme which can bind to a substrate to form a product. Once the product is formed, the enzyme can either react with the substrate to form the product, or can either unbind and start the reaction again. In the classical scheme, the classical result assumed constant rate for each step of this chemical reaction. And the classical result stated that trivially, the optimal reaction occurred where the unbinding rate is 0. But actually, people have shown that if you relax the hypothesis of exponential waiting time, there can be a situation in which you can actually speed up the reaction with a non-zero unbinding rate. So actually, this is a case where restarting the process can improve the completion time of your experiment. So first of all, let me be a little bit, but not too much more specific. And so let's see a specific case where restarting is actually useful. So suppose that we have an experiment. As I said, we observe an object whose dynamics is described by some complex law that we don't really know. And so we treat it as a stochastic process. And we have to measure the time that it takes for this stochastic process to reach a given outcome. Let's say that we are considering a one-dimensional system. We start from a given point, and we have to reach for the first time another point that we have set at the beginning. So we treat in other words, we are looking for the first passage time of this stochastic process to this target, let's say. And suppose that we know the first passage time distribution of this problem, and we also define the survival probability as the probability that the search has not been completed up to time t. Of course, as you know, in physics, when we talk about stochastic process, the paradigm is Brownian motion. So if we consider the problem, for example, for Brownian motion on a semi-infinite line, let's say that we start from a point which we fixed as the origin of the coordinates, and we have a target at position x, so a distance x from the origin. We know, of course, it's a classic result from probability theory, how to derive the first passage time distribution of this problem. But we also know that in this very simple case, very simple yet paradigmatic case, the distribution has a particular feature of having this power law decay, such that the first moment of the distribution is not defined. And for what I said at the beginning, this is kind of a problem, because at the beginning I said that the search efficiency is measured with the first passage time, but for a system like this, the first passage time is not defined. The average first passage time is not defined, sorry. The first moment of the distribution is infinite. So if we have a system like this, what the question is what we can do to obtain a better search efficiency. As I said, the answer is we just restart it. We let it go for a while. If the search is completed, we are happy. Otherwise, we just restart and we begin again. So the idea of resetting is simple as that. It's nothing too complicated. We start the process and we set a waiting time. We observe up to this waiting time. If the target is reached within this time window, we are okay. Otherwise, we restart, we stop the dynamics, we take it back to the initial position, we draw another waiting time, and we repeat the process up to the point where the target is reached. So in this simple setting, at the end, we will have a random number of failed attempts where we had to restart. And then we have the final successful attempt. And we assume that we assume that this waiting time for a start are independent and identically distributed random variable. For now, we assume that these random variables are described by a probability distribution such that the average waiting time is finite. And of course, and we also define this, which will be used for later. We define, we know, of course, the probability density function of the waiting times. And we also define the probability that a resetting event happens after time t, which is this big phi of t here.
What kind of situation do you want to model by taking this waiting time? So this is the threshold time before which after which you reset the system. Why don't you take the same time every time? So you repeat the experiment.
Yeah, sure. Oh, okay. I will answer later, but this can actually be there. I can anticipate the answer if you want. Actually, it is also be the case that you are mentioning, the case with fixed time window. It has an advantage actually with respect to the case where you take just some random waiting time, but it can also have a disadvantage. Okay. So suppose that we call, so let me call key 0 of t the PDF of the t0, which maybe I didn't say it, but is the time of a unsuccessful attempt, and key 1 the PDF of the time of the last successful attempt. And let us call E1 the probability of a successful attempt. And of course, we assume for obvious reason that this probability is larger than 0. Otherwise, we will keep on restarting till the end of time. And so in this simple setting, the the first passage time distribution in the presence of resetting, I mean, follows directly from the definition. You either is equal to K1 if there were no unsuccessful attempt, if you were so lucky that at the first try you already got to the target. Otherwise, the convolution between K0 and K1 if you just had to restart once, and so on and so forth. So you can have a number of NF of a number n of unsuccessful attempt, and you have then the interval described by the random time of by the random distribution of the successful attempt. So it's just a convolution form. And of course, as I said at the beginning, I'm interested in the, okay, I can derive the full distribution. I can write it in Laplace space explicitly, but I'm interested in the, for now, in the first moment. And the first moment is simply equal to the expected number of failed attempts times the expected time of the expected duration of the unsuccessful attempt plus the expected duration of a successful attempt. We can also be more complex than that because we can also be more specific because recall that the time of an unsuccessful attempt is equal to the resetting time whenever the trajectory doesn't reach the target. And so we can immediately write, since the waiting time and the waiting time for a reset and the dynamics are independent, we can immediately write the distribution of T0. And the same holds for T1. And so it follows that basically the first moment of the first passage time in presence of restart is just equal to the expected number of tries times the expected duration of an attempt, either be successful or unsuccessful. So very easy formula. I mean, it also follows from basic probabilistic arguments, but okay. Now, of course, in the physical literature, you sometimes also want to consider some specific problems. And so you want to particularize the problem to some explicit form of waiting time distribution for the resetting. And of course, in physics, one of the most common is when we talk about waiting time distribution is the exponential one. So many works have been done with assuming exponential waiting time distribution for reset. And in this case, everything becomes particularly easy because if you go to Laplace transform, everything is just written in terms of Laplace transforms of the first passage time distribution of the, let's say, original process without resetting. And so we have, let's say, a more explicit expression for the expected first passage time in presence of resetting, which is written just in terms of the Laplace transform of the first passage time distribution of the underlying process without resetting. And as I said at the beginning, we are particularly interested in the case of Brownian dynamics in one dimension. And in this case, what happens? We just use the formulas before, and we find explicitly what is the solution of the problem in this case regarding the expected first passage time. And the consequence is that, okay, we see that now the expected first passage time is finite for any given resetting rate. But the observation that actually led to a growing interest in this topic is the fact that there is also the possibility to minimize this expected first passage time with respect to the in other words, there exists some optimal resetting rate that makes the expected first passage time minimal. And of course, in this case, you can actually, if you want, you can compute it explicitly. It's you have a well, I mean, you have an explicit solution, you can compute it analytically. But the point is that this observation led to people wondering if this was something that could be generalized to other kind of waiting time distribution. And so people have tried many kind of waiting time distribution, or also have tried to apply this resetting to other kind of system beside Brownian motion, etc. And to answer now the question you were answering, another well-studied kind of waiting time distribution is the one that is referred to as sharp resetting in the physical literature, where you just fix a time one for all, and then you reset every time at that point. And people have been able to show that if you use for Brownian, for diffusion processes, this kind of strategy, you obtain features similar to the previous one, in the sense that you always, for any resetting interval, you obtain a finite expected first passage time. There is a minimum of this first passage time, expected first passage time curve. And actually, people have shown that this strategy is the optimal one among all the possible strategies, because it's the only one, is the one that minimizes the most the expected first passage time. Oh yeah, sorry. I mean, no, I'm just talking about this context where you don't couple the path and the waiting time. Yeah, sorry. But I mean, the downside of this strategy is that this is good, of course, for Brownian motion, because for Brownian motion, for any given interval and whatever distance you have the target, you have always a positive probability of reaching the target in that given interval. But you can see, if you consider some dynamics which is constrained to move with some fixed speed, fixed velocity, then you have to know in advance. You have to choose the resetting interval in such a way that you don't make the probability of reaching the target before being reset equals to 0. Whereas in the exponential case, you don't need to do that. Okay, so now the point is that this is true because we assume at the beginning that you can just restart every time you want up to the point where the target is reached. But there are many situations since at the beginning I talked about chemistry or molecular dynamics, there are many situations where the object that you're observing are subject to decay. And so you don't have an infinite number of tries. You can try a set, you can try for a given number of time, and then after that, your particle may decay. And so the question is, for this kind of system, can resetting still be something that is useful? And if yes, what is the limitation of the strategy? I mean, can I use it every time? Is it every time good, or sometimes it's good, sometimes it's bad? Of course, now in this case, let me remark that the question becomes twofold, because in the previous case, we started with a stochastic process where we assumed that the probability of reaching the target was 1 in absence of resetting. And after including resetting, we still had a process will reach the target with probability 1. In the case of a mortal system, we have typically a process that where the probability of reaching the target is smaller than 1, because there is also the probability that the particle decays before reaching it. And so when we introduce resetting, what do we do to this probability? Can we increase it in some way or not? And second, of course, we're still interested in the expected first passage time for those particles that actually can reach the process before decaying. So we ask how resetting affects the first passage time of these particles. And we will suppose that now that the particle has a finite lifetime, and we will mod it as a random number, and we will also in this case assume that the process that defines the lifetime of the particle is independent from the dynamics at the resetting mechanism. And but of course, let me mention that there are cases where it's actually interesting to couple the lifetime to the dynamics. For example, where you are modeling the lifetime in such a way that is describe the life of a particle in some strange environment with holes. So you have some distribution of holes all over the space. And if you imagine that the particle, as soon as it reaches a hole, it disappears, it dies. In that case, you will need to include some coupling between the dynamics and the lifetime. But in this case, we just do the simple case and we take the lifetime completely decoupled from the dynamics. So in this case, the first passage time distribution is simply the product of the probability of surviving up to a given time t, and the density of, let's say, the whole problem in absence of mortality. As I said, there are two questions now. We ask if this resetting can increase the probability with respect to the reset-free system, and we also ask what we can do with regard to the expected first passage time. And in the following this talk, I will limit myself to the case of constant resetting rate at constant mortality rate. So exponential waiting time distribution for the resetting times, and exponential distribution for the lifetime of the particles. So in this case, it's very easy to write the first passage time distribution in presence of mortality and resetting, because if it is just the product of the old one times the probability of not decay up to time t. And so if we go to Laplace transform, it's particularly easy because it can actually be written in terms of the Laplace transform of the solution of the old problem. Now, for exponential resetting, we can use, let's say, we manipulate just the two results that we obtained earlier, and we follow a simple result that connects the Laplace transform of the first passage time PDF in presence of resetting with the expected first passage time in presence of resetting. And why do we need this? Because now if we ask if resetting can increase the probability, let's say the probability of success, the probability of reaching the target before decaying, this is actually equal to the Laplace transform of the probability density function of the problem in presence of resetting, evaluated at the Laplace variable equal to mu. So if we use the result of before, we just have that the probability in presence of mortality of reaching the target is connected very easily to the expected first passage time that we obtain in absence of mortality. So in other words, we have just a direct connection between the problem in absence of mortality and the problem in presence of mortality. So we have already, we have straightforwardly an answer to our question. Can resetting increase the probability of success? Yes. Whenever the first passes time could be more, in absence of resetting could be minimized, then the probability can be maximized. So if we know the optimal resetting rate that minimized the mean first passes time in absence of mortality, we automatically know the optimal resetting rate that maximizes the probability in presence of mortality. But this also tells us that this can be done only if the resetting rate doesn't surpass this, only if the mortality rate does not surpass this optimal resetting rate. So we also have a threshold for this, for the mortality rate for which we can actually use resetting to increase the probability. Of course, we can use, since we have talked about the problem of diffusion, we can use these results for diffusion. We just to look at what expression do we have, but actually this is not necessary. Of course, we have the explicit form for the probability, and we see that whenever the mortality is higher, this R0, the probability is just a monotonically decay function of the resetting rate, whereas if the mortality is lower than this R0, we have a region where the probability increases, reaches a maximum, which is at position R0 star minus nu, and then it decreases. Of course, we should not limit ourselves to the specific case that I consider. We can consider other examples. Now I'm just showing a couple examples for a simple reason. The first example is the case of a Brownian dynamics inside an undimensional ball. And in this case, we are interested in the first passes time of the particle outside the ball. And why I'm showing this example? Because up to now, I only dealt with cases where resetting was certainly advantageous. I'm in the case of infinite lifetime. But there are actually, and the reason was that the system in absence of resetting had an infinite expected first passage time. The distribution of the first passage time had a power law. And so in that case, the expected first passage time was infinite, and we saw that with resetting, we can make it finite. But one can ask, okay, but if the expected first passage time is already finite for the system without resetting, what happens in that case? In that case, the answer is it depends. It depends on the statistics of the first passage time of the system, of course, but there are situations where even if the process has a finite first passage time in absence of resetting, resetting can decrease it. And this is a case. But we can show that in this case, in the case of the particles inside the ball, it depends strongly on it depends on the initial position. One obtains that resetting can improve the search efficiency only if the particle starts its dynamic in a outside an inner region of the ball of radius inside the critical region outside the critical region of the inner of the ball. And this critical region is always, of course, a ball, and is such that for a fixed dimension n, the radius of this inner ball is equal to the radius of the outer ball times this coefficient that depends on n. So let me rephrase it because maybe I was a little bit confused. If resetting starts outside this inner region, if the particles start outside this inner region, their resetting can be advantageous. Every time the particles start inside this region, inside this ball, inside this smaller ball, then resetting can never help. It only hinders the escape process from the ball. And actually, this tells us that if we now consider a mortal system, for whatever mortality we choose or we have for the particle, if the particle starts inside this forbidden region, then there's no possibility that resetting will increase the probability of escaping before decaying. And another example that I want to mention is one where we modify the dynamics instead of considering Brownian motion. Now we consider the telegraphic process. The reason why I want to mention it is that because in the physical literature, many people use this model without actually calling it telegraphic process, even if, I mean, it's a very old model. They prefer to call it random tumble particles for some reason. As far as I understand, because this model is used to describe the dynamics of some active matter. And so they call this random tumble particle because it describes some particle that moves on a, let's say, on a straight line for an exponentially distributed waiting time, and then at some point is just move in a changes randomly the angle of motion, then starts again for an exponentially distributed waiting time, and so. And they call it in this way because this model is used to describe the dynamics of active model dynamics of active matter, but actually it's very old. It's a telegraphic. It's called telegraphic process in the mathematical literature, and of course, the result it's old here as well, and so we can use it to, if we want to derive what happens if we take this telegraphic process and we consider resetting for it, and we also include the possibility of considering a mortal particle, and we obtain basically morally the same result. So of course here I just did some plots for reference, but I mean nothing. These don't tell you nothing new. And so the second question regards, as I said, how the resetting can influence the first passage time. Actually, now we talk about conditional first passage time because in this case we measure the first passage time, of course, only on those particles that reach the target before decaying. And actually, again, this is very simple in the case of exponentially distributed resetting and mortality, because the expected conditional first passage time can be directly related to the probability of reaching the target. And so in this case, we have a very simple formula. And again, this formula is related just to the expected first passage time of the problem with resetting, but in absence of mortality. So once again, if we can solve the previous problem, we can solve it straightforwardly, this new one. Now, of course, what we can do with this expression, we just look at the behavior at the, let's say, what happens for in the limit of 0 resetting rate, and what happens in the limit of infinite resetting rate, just to give a preliminary idea of how this let's say this thing work. And of course, we in the limit of 0 resetting rate, we do not obtain a surprising result, because of course we expect to obtain the result in absence of resetting, and this is what we obtain, of course. A little less trivial is what happens in the case of infinite resetting rate, because you may remember from the plot, even if I didn't mention it, is that in the absence of mortality, we observe like some, let's say, U-shaped curves. And so in the limit of infinite resetting rate, we observe that the expected first passage time was going to infinity. In this case, instead, we obtain that typically the conditional expected first passage time reaches a finite limit. In the case of diffusion, this finite limit coincides precisely with the average lifetime of the particle. In the case of run and tumble particle, instead, this finite limit is still the average lifetime of the particle, but to which you have to add a contribution. And basically, this contribution that you have to add is basically the contribution of the last successful attempt. In the case of diffusion, this contribution can go to 0. In the case of the telegraphic process, instead, it doesn't go to 0, because the telegraphic process is a process where the movement is constrained to happen at finite speed. So if you have a distance x from the target, you cannot reach the target in a time. And if you call c the speed, you cannot reach the target in a time smaller than x over c. But anyways, in both cases, you observe that in the limit of infinite rate or infinite resetting rate, you observe a finite limit. And so now the optimization problem becomes much less trivial, because in the previous case it was very easy. You just had a U-shaped curve, so you may say, oh, this curve will have a minimum. But in this case, it's not guaranteed that you observe a minimum. And actually, depending on the mortality rate, you can observe very different behavior of this curve if you think about it as a curve as a function of the resetting rate. So if you fix the mortality rate and plot the curve, you will see that depending on how you fix the mortality rate, you will see quite a different behavior. Of course, since I talked about the other example here, I just reported the explicit result for those examples, but I just like to show you a picture of the case of Brownian searcher to show you how this expected first passage time look like for different mortality rates. And so if you're wondering in which case actually we can take this curve and find a minimum, actually not just a minimum, it is not sufficient. I mean, we want to find a value which is smaller than the case in absence of resetting, of course, because otherwise it will be pointless. And we actually see that I cannot here, unfortunately, I don't have analytical proofs, but you can actually see that a minimum appears only when the mortality rate is low enough. So you cannot think of minimizing the expected first passer time when the mortality is very high. And so I did this test basically by plotting the curves, and what I see is that actually what I was saying, as you decrease the mortality rate, you see this minimum that you can actually reach by tuning the resetting rate accordingly. But as the mortality is increased, this minimum, you have this transition, and the minimum slowly disappears, and then after that you don't observe minima anymore. So you cannot minimize the expected first passer time. Okay, but as I said, for low mortality rate, you can do it. And now the question is, okay, but if I can minimize if I can maximize the probability, and I can minimize the first passer time, can I do both at the same time? And the answer is no. You cannot. If you look at the derivative of this curve, I said no, but it's not really true. If you look at the derivative of this curve, you see that if you remember that you could maximize the probability where you could minimize the expected first passer time in the absence of mortality. So if you plug on the left-hand side of this equation the value that maximizes the probability, the left-hand side is certainly equal to 0. But if you want also but in general, this point won't be a critical point for the expected first passer time in presence of mortality, because you will also need the second derivative of the first passer time in absence of mortality to vanish. So typically, a point that maximizes the probability is not also a point that minimizes the expected first passer time. So in general, the answer is that if you have a practical problem, you have to think and you have to optimize it. Typically, you will need to think what you actually need to optimize. Do you really need to optimize the probability of completing the process, or you need to optimize the completion time of a successful process? And for this, I actually still don't have many results, actually, because I haven't had the time to think about it, but it's something I'm working right now. And also, I want to say that, okay, all these results are easy because I used the exponential distribution for waiting times, exponential distribution for the waiting time for a reset. But actually, it will be very interesting to generalize this to other kind of waiting time distribution and distribution for the lifetime. Before concluding, let me just say that in this talk, I've talked about stochastic cell processes and the effect of resetting on those stochastic cell processes, but resetting has not only been studied for cell processes. The effect of resetting have been considered also for other properties of the stochastic processes. And for example, one thing that one can immediately ask is, if I take Brownian motion and I imply resetting, how does the probability distribution of the position at a given time changes? And actually, this is another very nice result, because in absence of resetting, you have your well-known Gaussian distribution. But actually, when you introduce the resetting, now I'm talking about still talking about the exponential waiting time case, you can reach actually a stationary state of non-equilibrium, which is described by an exponential profile. And so this is another interesting reason to study resetting, because it's a very straightforward way to study non-equilibrium steady state. And other problems related to it are, of course, that if you want to apply to real physical systems, this is a oversimplified picture, because you say that you restart the process, you stop the process, and you immediately take it back to the initial position. But if you had to do it physically, you will need to take into account that from a given position, you have to take it back, the particle. And so this requires a time cost that, of course, will change the statistics of the first passage time. And so people have tried to implement different ways of taking into account this time cost. But in many of these cases, you still can observe, one interesting result is that you can still observe the curve with the same features, and you still have some optimal rate that can make you the search, the expected first passage time minima. And among these, there are many other cases where resetting has been considered. And recently, I know that's also someone from the mathematical literature has tried to work on, Marco Zamparo have tried to work on system with resetting, especially Brownian motion for resetting. And of course, you can use tools from probability theory to avoid limiting yourself to exponential times that are mostly used in the physical literature, and you can be more general and prove much more better result. So that's all. Thanks for your attention.
50 minutes, completely optimized operation.
Yeah.
Okay, are there any questions?
Okay, where do I see? Actually, the first paper that proposed resetting was a paper about stochastic algorithms, stochastic Las Vegas algorithm, which is a paper that is always referenced in every physical paper that deals about resetting. Of course, as you said, finding a physical application is very hard for the problem I just mentioned, that you have to think about taking a particle and putting it back to the initial position. This has two problems. One is the problem that I mentioned, that you need some time to do it. You need some physical mechanism. People have tried to think about it. For example, they have realized it's some kind of resetting system by using optical traps that can switch on and off. But the other real problem is that when you take the particle and you retake it from to the starting point, you will never be able to put it exactly on the starting point. So you also have to take into account that you have some distribution of the resetting position, and you have to modify this simple result taking into account all these facts. But of course, it's not a trivial it's not a trivial problem to do, to actually take a real physical system and apply resetting. Also, another problem related to biological system is that the environment changes. So you cannot actually say that if you reset, you have restored the initial condition, because the system can decay. And so there are some.
can only do so many trials, and you might want to optimize a combination of the expected time and fluctuation around the expected time, or the median, because you don't, so the expected time gives you little information in certain cases. Have you done, or do you know any other type of optimization?
I can actually tell you that in this case of resetting, it is not the optimal resetting rate. It is not just the rate that minimizes the. It's not just about the first passage of time. It's actually, people have shown that for system like that, I'm not talking about mortal system, which is a completely different story. For system like that, the resetting rate is the rate that actually makes unitary the ratio between the variance of the first passage time and the average first passage time. So you can make this ratio smaller than 1 or bigger than 1, depending on your needings. But actually, say this universal property has been proved for many systems. So of course, you can think of much general strategies, but for now, I don't think people have thought about that. So in that case, of course, it can be interesting to see.
In terms of expected time, you don't lose in terms of the ratio stays the same in this strategy.
Yeah, I mean, no, what I was just saying is that when the rate is optimal, the fluctuation and the average is unitary. You can have a situation where the fluctuation are larger than the average, or of the opposite. But I mean, as far as I understand, the question is if there are other criteria to optimize the search rather than the first passage time. And I mean, I don't know. I actually don't think people have worked on this field. That they mainly have worked on the first passage time. I think it could be something worth studying, because, of course, as you said, it's not always the first passage time that is the important thing. Yes, sure.
Right. Thanks, Michael, and thanks for the organizers for giving me the opportunity to give a talk at the conference. And I've given this talk 3 weeks ago. I've made some changes, and I see some audience members who have already heard the talk. And I gave this talk last year also, but with some errors in the dynamic seminar here. So I've corrected all the errors, and we managed to correct all the errors. Yeah, so this is joint work with Tanya Schindler, who's here, and I should thank her for introducing me to this line of problems. So the goal we had was to prove what we call the central limit theorem and the mixing local central limit theorem. You've heard these two terms during previous talks. For the sampling of the Lindelöf hypothesis, I will explain these terms in the next few slides. So the outline of the talk is, okay, I'll first introduce what sampling the Lindelöf hypothesis mean. And then I will mention the main results that we obtained. And then I will mention some abstract results that are already known and modified to our context that through which we obtain our results. And then since we'll be using trans-operator techniques, we will be also introducing some new Banach spaces. So I'll talk about these Banach spaces, and then I will give you an idea about the proof outline through how we prove the results using the abstract results. Okay, so what is sampling the Lindelöf hypothesis? So let zeta be the Riemann zeta function defined by this summation and by its analytic continuation elsewhere except at s equals 1, the standard Riemann zeta function we know. And then what the Lindelöf hypothesis states is that on the critical line, where the real parameter is equal to 1/2, the values of the Riemann zeta function grow like t to the epsilon for all epsilon greater than 0 as t goes to infinity. So this is like sort of a sub polynomial sort of a growth. And the best estimate so far is due to Bourgain from 2017. And his result tells us that epsilon can be chosen to be greater than 13/84. And this will be relevant in the next slides. So this is the state of the art about the Lindelöf hypothesis. And the Riemann hypothesis implies the Lindelöf hypothesis, but number theorists actually use them in certain cases interchangeably for certain applications. And this is one of the reasons why Lindelöf hypothesis is important. And even though, we know that the Riemann hypothesis is there have been a lot of attempts to prove the Riemann hypothesis, and there have been attempts to prove Lindelöf hypothesis as well, but these are analytically sort of very, very difficult problems. So what number theorists do is they introduce randomness to the problem. And the goal is that, okay, the hope is that maybe it will, of course, it'll, in principle, it will simplify the problem, and in practice also it does, and then it might provide some insight to the original analytic problem, right? So what some number theorists have done is that they've studied the ergodic averages of the Riemann zeta function on the critical line, right? So which I call zeta 1/2, right? But if we want to obtain some insights about the original conjecture, because the conjecture is about values at infinity, right? If you are considering ergodic averages with respect to some stochastic process, right? So the stochastic process should preserve a measure which is heavy-tailed, because we should be sampling values with high probability at infinity, right? Like, so for example, it should not be that satisfies, that has like sort of exponentially small tails, because then basically you'll be sampling from a compact neighborhood of around the average, right? So if it has exponentially small tails. So we should be cautious so as to what what stochastic processes we use. And one good candidate is the Cauchy random walk. And Weber and Lifshitz have proved this strong law of large numbers for the Cauchy random walk. So this is the Cauchy random walk, and they have precise asymptotics through, they obtained this by analytic means, using some estimates about the value distribution of, certain expressions related, sorry, not expressions, certain formulas related to zeta 1/2. And also this result was later generalized by Shirai when xk is not only the Cauchy random walk, but any alpha stable process where alpha is between 1 and 2. And I think maybe not this week, but last week we heard some talks about alpha stable processes also. And since xk's are heavy-tailed, that means, for example, if it's alpha stable, symmetric alpha stable process, then if we take p to be the integer part of alpha, then we know that the pth moment is not finite. And what our original goal was is satisfied, that we sample with high probability from the tails, right? So what this result tells you is that the values of Riemann zeta function on the critical line are small on average when t is very large. So this is sort of one way to interpret this result. Okay. And can we say more? So that is also, so one problem. I mean, maybe you can prove some sort of a central limit theorem type result here, but I couldn't find anything in the literature to consider the value distribution around the mean, right? So is there a dynamical equivalent? The answer is yes. I won't be here speaking if there is no equivalent. So if you consider this Boolean type dynamical system, so it's Boolean type, we call it Boolean type because I'm sure you know about the Boole's transformation, right? Without the 1/2. And as soon as you put 1/2, it preserves a heavy-tailed ergodic probability measure, which is the standard Cauchy density. And this, I mean, the Riemann zeta function on the critical line is in L2 of this measure, okay? This probability measure. And Stewarding, another number theorist, proves the strong law of large numbers, which is the ergodic theorem for sampling the values of Riemann zeta function on the critical strip along the trajectories of this dynamical system. And we know that this is a ergodic probability measure. Trajectories over a long time distribute according to this measure, right? This invariant measure. So what we are doing here is also sampling values of the Riemann zeta function on the critical line, but at infinity, you know, because this has according to this measure, but you know, this has heavy tails, so we are still satisfying the actual requirement in some sense, right? So this is some background. Can we quantify this convergence further? Yes, we prove a central limit theorem, and okay, and mixing local central limit theorem. But when I get there, I will tell you that there's a little caveat. I will tell you we don't actually precisely prove it, but I will tell you what is the catch is. Okay, but we prove the central limit theorem for sure. But in the mixing local central limit theorem, there's a slight problem. Okay, so the main results. Before that, I should say, so the results that we state are a sort of a particular corollary of a more general result. But I mean, I didn't want to bother you with all the technical details and everything because this is the last talk. So I will only mention the sort of the application that we had in mind, right? So okay, so consider a function on the real line which has these decay properties. So growth properties. H grows like x to the u and at infinity. And also the derivative grows like x to the v, and u and v satisfy this relation. And because of Bourgain's estimate, we will have this with u certain value. And then of course, Bourgain proves more. It has, he has results for derivatives as well of the Riemann zeta function on the critical line. So because of that, we have this kind of an estimate satisfying this. So the real part, the imaginary part, and the absolute value of the Riemann zeta function on the critical line is an example of such a function. Okay. And the standard notation, we subtract the mean, and then this is the Birkhoff sum along the trajectories, and let curly n denote the standard normal distribution, and then Z is this, and I will come to that later. Maybe you already know about something about the Boolean type transformation I mentioned. When I gave this talk in Roscoff, John Aronson was in the audience, and he was like, immediately, yes, sir. He recognized why I mentioned this, but yeah. Anyway, so we have the central limit theorem. When H bar is not a Fico boundary, then there exists a non-zero sigma, and which is finite, such that the central limit theorem holds. Okay, so this is a standard, the central limit theorem we know. And actually we can show by considering values of the Riemann zeta function on the critical line along trajectories of periodic orbits, that phi that not phi yes that is not phi homologous to a constant. This can be done. So this result holds for in particular for the real part, imaginary part, and the absolute value of the Riemann zeta function on the critical line. And this sort of quantifies the Studing's result, right? Even further, the value distribution in some sense we understand better. And also we, for observables, H such that like a more restrictive condition, if you have this more restrictive condition, then we can show the precise error of this central limit theorem. I mean, if you know, it's called the first order Jyot expansion. So we can, once we subtract, we know the exact error term up to a second order term we can describe. But unfortunately, Bourgain's results are not good enough to give us this for the real part, imaginary part, and the absolute value of the Riemann zeta function. So if the analytic results become better, we can obtain this, the high order expansions. And in fact, if the Lindelöf hypothesis is true, we should have all order Jyot expansions, right? We should be able to write the error term here as an asymptotic expansion, but we don't know whether the Lindelöf hypothesis is true. So this result was obtained to, in some sense, get an idea whether the Lindelöf hypothesis is true. So it's sort of it's counterproductive to say the other way. But anyway, so, and the other thing is that for different L functions, I mean, there are other L functions, this might hold, but the only thing we have to check is whether H satisfies the previous relation, that is U times 2 plus V is less than 1, right? The previous condition, not this strong condition, where U and V are the growth rates of the function and the derivative, I mean, the observer, right? So in that case, if such L functions satisfy, I mean, any other L function satisfy this, then we immediately have the central limit theorem from our results. Okay, right. So this is the central limit theorem, and this is the mixing local central limit theorem. So this is like a long equation, but I'll try to explain this. So V is some compactly supported and continuous function. So this is where it becomes local. So you localize values of the Birkhoff sum, right? So you're looking by using a compactly supported continuous function. And the mixing part comes from this. Here you keep track of the initial point. Here you keep track of the end point. I think I had this mistake even in, okay, this should be phi. My bad, this should be phi, not shy. Okay, and so it keeps track of the end point and the initial point. So this is, in some sense, why we call it the mixing local, and local because of this compactly supported function. And psi appears here, and you'll see later why psi appears here. And here this classes C0 and L1 can be replaced by, C0 can be replaced by a larger space. Then we have to deal with where W is, but we know precisely how to deal with this by the choice of U and how W changes, but I will just, I just wanted to state it in the most simplest form. And then the catch, as I said, is that it is more difficult to conclude that the real part, imaginary part, and the absolute value of the Riemann zeta function on the critical line is non-arithmetic. I will define what non-arithmetic is in later, but the guess is that we don't even know whether the value distribution of the Riemann zeta function on the critical line is dense in the complex plane. We know if for example, this is a well-known result, maybe This is fine. So if I take the, sorry, I can't write Riemann zeta function, maybe see. Hopefully I will write it and then I will, this sigma between 1/2 and 1 and T in R. So fix some sigma between 1/2 and 1. And then hopefully, okay. Right? And then when I vary T, the value distribution is dense in the complex plane. This is a known result. But then when sigma is equal to 1/2, this is a conjecture, it's not proved. So we don't know whether the values are dense. So up to a co-boundary term, maybe it's useful to know that it's dense. Maybe we can use that to numerically show that this can't be non-arithmetic, but we don't know. So sorry, I pressed this. So we don't know whether the real part, imaginary part, and absolute value of Riemann zeta function are non-arithmetic. If it is, then the result is true. If not, then we have to maybe prove a local central limit theorem or something like that, because up to a co-boundary values will be on a lattice. So this is a different story. So I will not say anything more about that, but it is believable that it is non-arithmetic. But yeah, but we have more. Like we can show that if H bar is non-arithmetic, then this result holds, and it's a more general result, and we are looking at a dynamical system on the real line. Okay, so that's the catch there. Okay, so okay, I should. Okay, maybe any questions so far? No? Okay. So I will state the abstract results through which we obtain our conclusions. Okay, let me see. How am I doing on time? Okay, I've only taken 20 minutes. That's good. Okay. So the abstract results. So I will define some, to fix notation, I'll define some, state some symbols. So X be a metric space and with a reference probability measure M, and T is a dynamical system that is non-singular. So if a set has measure 0, then its inverse image under the dynamics will have 0 measure. Okay, this is standard. And M bar is an ergodic invariant probability measure of T, and M bar is absolutely continuous with respect to the reference measure with density rho M bar. Okay, so this is the setting. This is the dynamical setting. Okay, and we call an observable to be T cohomologous to a constant if there is some function in L2 of M bar such that H can be written as L composed with T minus L plus a constant. If C is equal to 0, we say H is a T co-boundary. And H, an observable, is non-arithmetic if it is not T cohomologous in that sense in L2 of M bar to a sublattice valued function, which basically means that there is no L such that this belongs to some constant translation of a lattice in R, right? So okay, up to a translation and rescaling, it's not Z valued, right? And up to a co-boundary, up to a translation and up to a rescaling, H is not Z valued, right? Okay, right. And T bar is the transfer operator of T with respect to M, and we encountered this object in previous talks, and it's defined as through the duality relation, right? So if H is in L1 and H star is in L infinity, M of T hat H times H star is equal to M is equal to M times M of H times H star composed with T. So this is a dual of the Koopman operator. So composition operator is called the Koopman operator, and its dual is the transfer operator. And in the case of expanding maps, we saw the formula in Roberto's talk. And we do this twisted transfer operator by twisting by this exponential factor, where H is our observable, right? And then we have a family of operators, linear operators. And the key relation that we all use in this business is this. The idea is that the characteristic function of the Birkhoff sum, okay, forget these two for now, V and U. V and U, you can take them to be one, can be written as an expression that involves the iterated operators. And then if the transfer operator the twisted transfer operator has a good spectrum, then we can sort of reduce this into basically the IID setting, right? So this is sort of the key idea in what we call the spectral approach or Nagy-Givac approach of proving these type of limit theorems. Okay, so this, and then if you want to prove sort of a mixing local central limit theorem, then you have to consider these two additional functions there, and then it also boils down to sort of an expression using this duality. If you sit down and write this, maybe you'll be able to obtain it. It's not a more difficult relation to obtain, right? But essentially, if you remember the IID case proof of the central limit theorem, it is essentially the same in this setting. We can sort of play around and with the spectrum of the transfer operator and then obtain this. But we are not using that for the central limit theorem. We are using a result due to Gordin. And what he states, this is proved using martingale techniques. The idea is that if your observable is in L2, and that this series, which is obtained by applying the transfer operator to this observable, converges in L2, then we have the CLT, and we have a specific, exact expression for the variance, and variance can be 0, and it happens only if not F, H is a T coboundary, and in this case we have convergence to delta at 0. Right? So this is Gordon's theorem, and it's very powerful because you only need to take something like this, right? And this is what we do. But of course, for that we need a nice Banach space, and that is sort of the bulk of the work that we do. We find some Banach space where we can show some good spectral properties of T hat and also the twisted transfer operators. Okay, so this is one result. So the only thing you need to remember is that this should converge in L2. Okay, right. And there's another result that we use for the mixing local central limit theorem from a paper of Irvi and Pène from 2010. And this is a bit more involved, so I will state, I'll go line by line in some sense. So we need two Banach spaces. Oh, I will maybe, because I have some time, right? So I'll take a few minutes to explain why this kind of a result is important, because so the idea is that these Banach spaces we use typically in Nagy-Givac approach are Banach algebra. So for example, C1 or BV. But if we cannot find good spectral properties on Banach algebras, then we need to sort of figure out, we'll have to use these type of inclusions, and I will tell you later, maybe you'll see a specific example where this comes in that this becomes important, like considering sequences of spaces like this. So we need two spaces, B0 and B1, each containing the characteristic function of the space, such that this inclusion happens. It can be some higher, I mean, it's better if you have some L2 or something like that, but it doesn't matter here. And this means that the identity is continuous from B0. Identity operator from B0 to B1 is continuous. And we need three properties about the trans operators. So the twisted trans operators should all be bounded linear operators on B0 and B1. And the map S going to T hat of IS, right? So where S is taken from the reals, and then this considered as a bounded linear operator from B0 to B1. So the topology on this side is a topology on the space of bounded linear operators, is continuous. And then we need that the iterated trans operator converges to the sort of the projection onto the top. This is the projection onto the top eigenspace. So if you know this, but then this, if you've seen this before, but this is also something that we should have, and this becomes automatic if you have a spectral gap and the trans operator has a spectral gap, and the top eigenvalue, which corresponds to the invariant measure, it's simple, right? So this will be automatic in B0, right? Okay. And the second statement is about some nice properties of the resolvent. And so the idea is that away from 0, away from 1, and this is away from 0 and away from 1, the resolvents of the family of twisted trans operators, right? First of all, they should be bounded linear operators on B0, and then their norms should be uniformly bounded in some sense. Okay? But this is a very general, I mean, this is maybe you think, okay, how do I check this? But you can check this if you prove something like Doblin-Forte-Lassoteo inequality, then it follows from that, and I will show you how we do that. And then also lastly, we need that the CLT that I mentioned earlier holds with sigma positive. So if these conditions are satisfied, then for U in B0 and V compactly supported, and any initial measure M0, probability measure M0, with W in L1 of M, such that W times M0 is in B1 prime, which is the dual of B1, the mixing local central limit theorem holds. So this is a very general theorem, right? And in order to apply this, we need to figure out the Banach spaces B0 and B1. Yes, sorry. Yeah.
Go back to the slide. The third hypothesis, the one that you commented on.
This one.
Automatically, M bar is the invariant measure corresponds to the invariant measure corresponds to
this, you mean this one?
Yeah.
Yes. I mean, but of course it should be simple, no? Right?
Yeah.
Yeah.
Isn't it the other way around too?
Yes.
See this as like the simplest hypothesis is right in the beginning would be left M bar B, but you wrote it in the third one. Somebody else wrote it in the third hypothesis. I don't know, maybe they're not exactly the same hypothesis.
No, because maybe if the dynamical system is not exact, like there can be eigenvalues which are on the unit circle, which are not just one, right? So
I mean, I understand you may not have a spectral gap and still have like all these defaults, but isn't this the same one? I mean, it's the same as formulated that way that I was puzzled.
I'll have to think about it, but yeah, okay.
Yeah.
Yeah, yeah. So I sort of, okay. So, well, okay. I stated this. So I said adapted to our setting. So, in the sense that certain things I've generalized, certain, like, you know, it's still in the paper by Irving Pène, but we can maybe talk to Francoise later. Yes, but yeah, yes, but yes, okay. And so, okay, as I said, so the main contribution of we do is introducing these Banach spaces, and so I will state the Banach spaces, and I will sort of mention where the inspiration comes from, and maybe alternatives, possible alternatives that we considered at some point, and then why, I mean, not why, like, I'll mention some alternative approaches, possible approaches we thought would work, but didn't work. Okay, so what are the Banach spaces? And these are generally called the generalized bounded variation. So what we consider first is the oscillation of a function. So let f be some measurable function, and the oscillation of that function is on a set S is the maximal difference between the values the function takes on that set. Okay, and then we define this new, it's not an operator, it's just multiplication by this guy, which basically what it does is it makes the values of the function, they pin them, the values of the function to 0 at 0 and 1. Okay, and you'll see why this is important later. Okay, and so, okay, these two are these, right? Okay, that's oscillation and R alpha, what they mean. So this sort of forces the values of the function to be 0 at 1, 0 and 1, right? And we are considering now value functions. Okay, okay, I should be 0, 1. Okay, 0, 1 into. Okay, right. And then we consider the oscillation instead of just the function f. We are considering the oscillation of R alpha of f. So we take a function, pin it down to 0 and to 0 at 0 and 1, and then consider its oscillation on a ball, and then average it out, and then look it at 1 over epsilon beta scale, right? And then take the supremum over all the possible epsilon between 0 and epsilon naught, where epsilon naught is sufficiently small. So for application, we know how to choose epsilon naught, but I will not deal with it. And then we define the norm on the Banach space to be this, where this is the alpha beta norm considered here, and this is the L gamma norm. And then the Banach space is where this norm is finite. Okay, and it's dual. We denote it by V prime. The norm depends on epsilon naught, but the Banach space does not. Meaning the functions in the Banach space does not depend on the choice of epsilon naught. Is the norm and the Banach space clear? So if you're familiar with the work of Benoit Sassol in 2000 on multidimensional expanding maps, then it's the same norm where without this R alpha. In that case, the space is embedded in L infinity, but because we here allow some f to have discontinuities, we allowed the function to have discontinuity at 0 and 1, and we just sort of force it to be discontinuous to disappear. We can allow f to be unbounded even on 0, 1. Okay, so this is what this does, and we do it because of the application we had in mind, right? Because if you map Riemann zeta function through this Z map I mentioned earlier, it will have oscillations near 0 and 1, unbounded oscillations of the form x to the alpha, x to the negative alpha, 1 minus x to the negative alpha. So we just sort of multiply by this guy to kill the oscillations, right? So this is what we do is because of the applications we had in mind. Okay, it's and also, so there are some good properties of these Banach spaces. When alpha increase, beta decrease, and gamma decrease, this inclusion properties are satisfied. Okay, so maybe you guess that something like this will be B0 and this will be B1, and this L gamma will be embedded in L1. So this is sort of the choice we make later. And then we also know that if I pick gamma bar such that gamma bar is between 1 over alpha and gamma, then this space is continuously embedded in L gamma bar. This we prove. And also the closed unit ball of V alpha beta gamma is compact in L gamma bar, right? So if you're familiar with the Nagieb-Givach approach, then this should be something familiar. And this will be our sort of strong norm, the norm here, and this will be our weak norm when we prove the Doblin-Fortel-Lossota-Yoke inequality. Okay, right. So that is for those who know already. So, but these are good properties to have, some useful properties that we find. But V alpha beta gamma is not a Banach algebra. Okay, so this is not a Banach algebra. So we need to do some more work. Anyway. And similar Banach spaces of generalized bounded variation were considered by Keller and then Benoit Sassol. And in both cases, the spaces were embedded in infinity. So, but for our applications, this is not good enough. There are some techniques. So when I was in Rome last year and talked with Carlangelo about this, he suggested maybe look at these two references where they use they deal with such discontinuities, but after some later discussions, we realized that it's not obvious to prove that the observers that we were interested in were in their spaces. So we don't know whether those techniques work, those spaces work, but it's not obvious. So we were able to prove that our space works, so it's good. And one key objection one might have, and I think this is the reason why Carlangelo was also not happy with it, because it's sort of tailor-made for the application, where like we know that what we consider these observers, this Riemann zeta function on the critical strip, when we map it to 0, 1, it will have some type of a singularity at 0 and 1. So at both 0 and 1, and we just try to kill it off. But what if you have a different observable which has different type of discontinuities, and so you'll have to change the space each time you do. But if you can come up with a space that deals with singularities in a better way, maybe it's a good thing. But for us, for our application, our spaces worked, so we were happy. But maybe it's a good idea if somebody can think about another space, another Banach space where the same problem can be solved without sort of knowing exactly where the singularities are, right? So, okay, this is a drawback of the Banach space we construct. But anyway, the proof outline, I think maybe, okay, this is good. Okay, I have 15, maybe 10 minutes, yeah. So there are two key ideas. Okay, the spectral techniques, and also the existence of a smooth conjugacy between the doubling map and the original guy, Boolean type transformation. So we reduce the problem to a 1 on 0, 1, where the conjugacy, this conjugacy Z. And we have the embedding of the Banach spaces. We pick these Banach spaces appropriately. And we show that the twisted transfer operators corresponding to the doubling map satisfy the Doblin-Fortel-Lossota-Yoke inequalities. And we also show that the family of twisted transfer operators are a continuous family of operators from B0 to B1. And we verify the conditions of the abstract theorem. So this is sort of the blueprint of the proof. This one? No, this is No. It's continuous, and then we know the unit ball is compact. That's no. We don't know the unit ball is compact, but like this not required. Sorry. Yes. So this is true. Like B0 going to B1, we don't know, because we don't know whether the unit ball in B0 is compact in B1, but we don't want it. We don't need it. We don't need it for the theorem. Right. So the conjugacy, so this is the conjugacy. It's a almost sure bijection from 0, 1 to R. And oh, this should be a comma. Yeah. Psi is the doubling map. And these two dynamical systems, the original dynamical system with the Cauchy density, is isomorphic to Psi with Lebesgue. And so, and also, I mean, this conjugacy relation holds. Both Z and Z inverse are measure preserving. Okay, sorry, measure preserving. I wrote the definition of what measure preserving means, but it's a key idea. I mean, if you take a pre-image of this under here, it's the same, and then Z inverse is the same, right? So this is what I've written on the mu. So these are good, and so because of this, instead of studying the original Birkhoff sums, we can study this Birkhoff sum for the doubling map with this new observable. And if H satisfies certain properties, then H composed with Z will satisfy certain properties. We will see later what these are. And also we have this, and also as a result of this, the asymptotic moments of these and asymptotic moments of these, they coincide, and this is also an important thing to when it comes to the limit theorems. But anyway, okay, this is good. And so the original observables that I picked like this, right, with this growth properties, then if I consider an observable on 0, 1, this transformed observable, it may have sort of this kind of discontinuity at 0 and 1, right? It might blow up. So that's why we do some damping, right? And then derivative also blows up like that, where B is 2 plus V, where you have, so this is exact. These computations can be made exactly, okay? And so, for example, the observables we need, like we wanted original results for, which is the Riemann zeta function on the critical strip. That's an example like this. Also, we can consider something like this, where when C is small, x to the minus C times sine 1 of x, something like that. An observable that oscillates highly near 0. And of course, you can analogously construct something near 1, but this is okay. So these are some of the examples of observables. And under these assumptions, the chain of spaces, we pick beta to be fixed, M to be larger than 2, so that this is embedded in L2. This is good. And then these trans operators for the doubling map satisfy the required assumptions. For example, this, okay, with IS should be bounded linear operators on our spaces. And also the multiplication operator going from this to this is continuous. Okay, so going from this space to this space, you increase alpha 2. It's not continuous from alpha 1 to alpha 1, but it's continuous from alpha 1 to alpha 2, where alpha 2 is larger than alpha 1. And this is because the space is not a Banach algebra. I mean, we cannot consider going from alpha 1 to alpha 1. We have to somehow get a larger space, like with a weaker topology. Okay, so this is This is there. And because of that, the twisted trans operators form a continuous family, okay, as required. And then we have uniform Dobrin-Fodor-Lossotto-York inequalities of this type with kappa, like the same constant for all S, actually, this kappa, and C tilde also. And we have these two, and combining 3, 4, 5, we get all the properties that I mentioned earlier through standard techniques. So this is all we have to verify to obtain to verify the conditions of Irvian Pène. And because this is embedded in L2, we have the convergence of the iterates of the and with the Lossotto-York inequality, we get that this when S is equal to 0, we have the convergence of the sum of the iterated operator applied to the observable. So we have the central limit theorem as well. Yes, I will stop there. For more details, you can look at our preprint, and thank you. Right. No, we need more. You mean here? No. So, okay. No, we have a theorem, but the problem is the state of the art about the Riemann zeta function is not good enough. So Bourgain's result is not good enough. We need, if you have more. So I will go back to the result. So if the analytic result improves, we have something. It's let me see. Let me go back. Yes, here. So if we can say that the Riemann zeta function satisfies this relation, actually you can say that if epsilon, I can't remember, like 13/84 is not enough. Yeah, maybe, yeah. But this can be checked if we know epsilon can be made smaller than maybe greater than 0.1, maybe, I don't know, not 0.1, 0.01, maybe something like that. Some threshold, yes, we will have, yeah. If it's 0, then if Lindelöf hypothesis is true, we have all order corrections, yeah. But yes. It's just multiplication by, we are just pinning the function to be, like, forcing the function to be 0. Where is it? Okay, later. Okay, Banach spaces. We're just forcing it to, so we look at how the discontinuity of the observers that we, like, so this has a x to the negative u, 1 minus x to the negative u type of a discontinuity near 0 and 1. So the power sort of a discontinuity, x to the negative u and 1 minus x to the negative u. So then we kill it off by this. So if it has a log type of discontinuity, you can, so you just kill it off by that. You pin it into 0. Yeah, so